our conference, the 12th edition of the International Micro-Air Vehicle Conference. And today I am thrilled to introduce you Tom Richardson, who is going to be our third keynote speaker, the first keynote speaker of the day. I'm going to read his biography, but first I want to say thank you to Tom for having accepted to be here with us and to talk about a very interesting topic. I think it's going to be very interesting for us who live here in Puebla, where we have nice volcanoes and mountains. But let me say first that Tom is a senior lecturer in flight dynamics and control at the University of Bristol with a PhD in nonlinear control system design. He specializes in the application of modern control theory and novel sensors to unmanned air systems. Tom has held an NPPL, a pilot license, for over 15 years, runs the University of Bristol glider flight test course, and has been responsible for US operations in multiple countries. He has been granted permission multiple times for beyond visual line of sight, quite impressive, operations, and holds the University of Bristol CAA US permission for commercial operations. He has also run flight demonstrations and test flights for DSTL, BAE systems, Kinetic, DSTL, and Rock Manor. Tom is also a founding partner of Perceptual Robotics, which has already recently been awarded Robotics and AI in Extreme Environments funding by Innovate UK for offshore wind turbine inspection. So after having said that, I don't want to take more time. So please, Tom, go ahead. And once again, you're welcome, and thank you for being here. Please, the floor is yours.
Brilliant. Thank you so much for that. Okay, I need to share my screen. Okay, Jose, could you just confirm if you can see the screen?
Yes, I do.
Brilliant. Thank you so much for inviting me. Thank you so much for having me and allowing me to present to you. It's an absolute pleasure to be here. I've been involved with IMAV for a number of years. I think it was 2005 or 2006 I traveled to the first one, which was in Europe. So it's a pleasure to be here. And I'm going to be talking to you about remote sampling and measurement of volcanic emissions using drones. So my primary research interests are in flight dynamics and control, particularly for agile vehicles. But we do quite a lot of work where we go out and we take our vehicles, our drones, into the field, and we use them to support colleagues, in particular with sort of challenge-led applications. And the one that I'm going to be talking about today is volcanoes. And you can see the Volcan de Fuego on the right-hand side, that's in Guatemala, and that's going to be one of the examples that I talk about today. And that particular image was taken from one of our own drones here at Bristol in a campaign that we had out there in March of 2019. Unfortunately, due to COVID, we haven't actually been on too many campaigns in the last 2 years, but we have recently been out to Guatemala again in October of this year. If anybody has any questions following this presentation, please feel free to email me at thomas.richardson@bristol.ac.uk, and I'd be very happy to answer them for you. So today I'm going to give you a little bit of my background. I'm then going to talk to you briefly about Ascension Island, because Ascension Island was the first place outside of the UK where we took our vehicles and we were applying them to a scientific challenge. I'm then going to talk in detail about Fuego volcano in Guatemala, and then I'm going to be talking about some gas measurements we did at Manam volcano in Papua New Guinea as part of a worldwide effort in terms of exploring the benefits of aerorobotics in volcanology. A lot of what I talk about today is some of the challenges involved with taking vehicles outside the country and deploying them in the field and flying them in remote and challenging environments. I'm also going to talk about a lot of the research challenges that fall out of doing this and some of the work that we're going to be doing in the future. The picture to the right-hand side there is of Manam volcano vent. That's in Papua New Guinea, and that was taken on a field trip that we had in May of 2019. And you can see the open vent of Manam volcano. We were flying through the plume, and we are doing real-time gas measurement in that particular plume. So my background is in flight dynamics and control. I've got a pilot license. I run the course here at the University of Bristol. And I've always been interested in taking vehicles outside of the lab environment and challenging them in, testing them in challenging real world environments. And things that work in the lab or work in simulation don't always work in the field. And it's finding out why they don't work and solving those problems that I find really challenging, interesting, and rewarding. On the right-hand side there is Perceptual Robotics. If anybody is interested, you can search for Perceptual Robotics in Google. But the purpose of that company that we set up with some graduates here from Bristol is using aero robotics for inspection and maintenance, in this case for wind turbine inspection. One of the reasons why I do this work is the people that you get to work with. And all three of the examples that I give you today came out of conversations with colleagues. So if I have one recommendation for you from today, it's to listen to your colleagues, to work with your colleagues. And if they have an interesting challenge, to go and work with them to see if you can address it. The second recommendation is to learn a little bit about geography, because in all three of these cases, it was places that I hadn't heard of before, actually, before I went. The first one was Professor Jim Freer, who until recently was a professor in geographical sciences here at Bristol. And he asked me if I knew where Ascension Island was. The answer is it's in the middle of the Atlantic, and I'll show you some slides on that in a moment. And he asked me if I was interested in using aerial robotics for atmospheric sampling above Ascension Island. And my answer was yes, of course. The second one that I've got there is Matt Watson, Professor Matt Watson from Bristol, Earth Sciences. And he said, do you know where Fuego is? Fuego is the volcano in Guatemala. And he said, I would like to sample ash from inside an ash plume over the top of Fuego volcano. And the third one there is Dr. Emma Liu from UCL, who's a lecturer at University College London. And she said, do you know where Manam is? And the answer is Papua New Guinea. And we did the real-time gas measurement over the top of that particular plume, or within that plume. And so the first set of thanks I'd like to say is to all three of these people for involving me in their work and offering me a challenge. And from the engineering perspective, there is nothing better than a science-led or technology-led challenge from which we can draw on our own research. So the first one of those three examples I'm talking about is in Ascension Island, and the challenge was atmospheric sampling. So we did this between 2014 and 2016. We traveled there 3 times. We built 3 multi-rotors. Sometimes in these challenges, people have a preconceived idea of what the best way of approaching it might be. And actually, we went through 2 or 3 different iterations and different approaches to doing this. The one that we decided on in the end was to fly multi-rotors up, and we needed to reach in the region of 2,000 to 2,500 meters above ground level. And then we took samples within, and you can see on the left-hand side there, you can see a drone there with a sample collection bag underneath a Tedler bag that we inflated at altitude, and then that air was taken back to sensors in the UK where they were tested for the content of those samples. We ended up in doing over 100 sample flights to altitude and collecting a number of different samples. It was great in the end. We won an award for doing this from the engineer, and there are a number of publications on it. And as we go through this presentation, I've highlighted some of the publications that we've had as we've gone through, so feel free to look those up. The challenges of flying outside in these kind of atmospheric conditions was highlighted to us. One such example you can see on the right hand side there, there's two plots. They're both on the same day in 2014. One was taken at 12:41 in the afternoon and one was taken at 2:36 in the afternoon. And you can see the prediction from the Met Office, given by the green dotted line. And you can see the solid dark green line. This is in terms of wind speed as we climbed up through 2,000 meters and went up to about 2,300 meters. And then you can see that actually the Met Office prediction hadn't changed much, but you can see the actual real world environment had. So working off the forecasts, up close on to 2,000 meters, we had 40-mile-an-hour winds at those kind of altitudes. So operating vehicles, and this is beyond visual line of sight because we couldn't see the vehicles at these altitudes, remotely reacting to the conditions that you're in and learning to generate flight plans and operate the vehicles in really quite hostile conditions is part of the process, and a really interesting and intriguing one. The other part of doing these kind of deployments is they're usually in the middle of nowhere. This was the site of operations that we had on Ascension Island, and we went out there, as I said, 3 times, and we were flying from this area here, which we picked up on a previous trip that we went out, and we looked all over the island for the best place to operate from. But it's not easy in terms of flying your equipment over there, in terms of deploying it and flying it repeatedly and safely in order to collect the data. But it's worth doing. By the way, the reason for doing it in Ascension Island, which I skipped over completely, is that Ascension Island, being in the middle of the Atlantic, has air masses that is coming both from the South Atlantic and also from Africa, depending on the altitude at which you're at. So you can actually sample different air masses by taking samples at different altitudes. And that's the reason why we were over there and why we were flying. You can see some of the results from the tests and the samples we took on the right-hand side, and you can see the ones in the South Atlantic air have a different composition from the ones in the African air above. So in terms of proving that the system worked, it was a great success, and also in terms of the science that we got out of it, our colleagues were also delighted with the results. From the operational side of it, one thing to highlight is that we were operating on Ascension Island, which comes under the Civil Aviation Authority rules and regulations, although a slightly different department. But we needed to get clearance from the CAA, brackets ASSI. We were also operating within 3 nautical miles of a US airbase, which provided its own challenges in order to get clearances. So another part of doing this work, which is really quite challenging, is liaising with the appropriate air authorities and also with the appropriate local law enforcement authorities, etc., to get permissions to do it. And so that's definitely one of the takeaways from this that we took forward into the other work. So that's really the first example of where we went overseas and we did this kind of work. The one I'm going to talk about now is Volcán de Fuego. So you can see a picture there on the right-hand side of Fuego. This picture is taken from the Volcanology Observatory. And you can see it erupts. And the beautiful thing about Fuego volcano is it erupts about every 20 minutes to 30 minutes. And you get this ash plume that comes out of it. And then it drifts downwind. And gradually the ash falls out as it drifts downwind. And the composition of this ash plume changes. So Matt Watson, who I mentioned to you before, we stood together at the bottom, we looked up towards the volcano, and he said, can you fly your vehicles up through that ash plume, and can you get me a sample of the ash that is up there? So bearing in mind, if I go on to the next slide, that the observatory is down in the left-hand corner here. We were looking up towards Fuego, and the distance is around about 8 kilometers, and the height gain required, and I'm mixing my units here, is 10,000 feet, so approximately 3,000 to 3,500 meters change in altitude and about 8 kilometers. So that's true BV loss operations there. So I said yes, and we went ahead and we made plans to do this. And I would like to take this opportunity of thanking several people. Here in the UK, we have the Research Council funding bodies. EPSRC funded this work through the Cascade Program Grant. So the Cascade Program Grant is 5 universities over 5 years, addressing a lot of the challenges involved with UAV or drone technologies and research. So it's funded from EPSRC through Cascade. I'd also like to thank DJAC, which is the air authority within Guatemala, who have been absolutely fantastic in supporting our work and working with them to get the correct permissions to do this. I'd also like to thank INSAVUME, which is the volcanology government department responsible for monitoring the volcanoes, and it has been a great pleasure working with them in order to try and support their efforts in understanding the volcano and understanding the risk that comes with it. There's also been a very large number of people involved in this work locally at the university, who it has been a pleasure working with. So we put it in as a case study, a sample of volcanic plume within the Cascade case study list. And then we went out to Guatemala and we started to operate the drones. So we have flown, this was a fairly early picture on the left-hand side, you can see here. And we've flown a number of multi-rotors, both from Acatenango nearby, but also fixed wing, and here are 2 of the fixed wing vehicles we've been flying from the observatory up to Fuego and up towards the target. So the target here are these ash plume, is this ash plume, which as it erupts, you can see this is from the most recent one, this is from the eruption before, and the eruption before that. So you're working remotely and you need enough information to tell you about the plume, to know when you're in it, to plan your flight into it, and to respond in real time to what's going on. This is an interesting short animation here, just to give you an idea of the power of drones, in speech marks, in terms of how they can support the work of INSAVUME. So this particular 3D model was generated from data from 2 cameras on board one of our vehicles, taken over the course of around about a 45-minute flight. And it covers an area that's around about 8 kilometers by 10 kilometers. And you can see the level of detail that is involved in here. So the ability for drones to capture detail in high quality data is absolutely fantastic for the purposes of INSAVUME and for monitoring the volcano. And just to go back to the reasons why we're doing this, as well as providing a lot of engineering research challenges, it also, in trying to help understand the risks, it can help support the local people. Within about 20 kilometers of the top of this volcano, you've got in the order of 100,000 people living. And unfortunately, 2 years ago, they had a pyroclastic flow which came down one of the barrancas, which I think it was this one, it came down. And unfortunately, a large number of people lost their lives in one of the villages. So that's the motivation for doing it. In addition to that, this particular volcano is within about 45 minutes drive of the capital city of Guatemala. And so it's like having an active volcano within Reading in close proximity to Heathrow Airport. So it obviously has a significant impact on their ability to fly international flights in this particular direction. So that's the motivation for doing it. Going into a little bit more of the engineering. So in this case, we needed to take samples. We created this means of collecting them. So these are what we call ash plume stub holders. And these stubs on the left-hand side, they're used by the military in the UK for collecting samples of aircraft and other vehicles. They're really quite small. They have sticky pads on the front of them. So we developed this mechanism to allow us to deploy them in flight. And you can see these mounted on top of the vehicle prior to launch. So we were collecting those on these stubs, and we can bring those back and use them with the electron microscope that we have in Bristol to analyze the ash that we collected. So concentrating on these, they're based on an X8 airframe. Wherever possible, we buy in airframes and then we fit our own avionics and write code for them. Just a side note, recently we've started developing our own vehicle because we haven't found a vehicle yet to buy in that meets our performance requirements that we need, both for this particular volcano, and actually I was talking to Jose just recently, one of the volcanoes in Mexico is going to be a brilliant target for doing some of this work on. So I very much look forward to collaborating with Jose in that area. And for those purposes, we're developing our own vehicle. With these though, your takeoff mass is around about 4 kilograms. We've looked at various different battery chemistries and types. We've had a maximum of about 75 minutes in flight, together with the sensors that we're carrying on board to fly there. Bearing in mind, it takes you in the region of about 20 to 25 minutes to climb up to altitude and to get to the top of the volcano. So that will leave you in the order of about 25 to 30 minutes to operate up there before you need to come back. So you're operating in the field, and you can see on the right-hand side there, that's the sort of base camp that we have and the kind of setup we have when we're operating. The other great thing about doing this work is that it involves teams of people, and I absolutely love working with great teams of people. So at a very minimum with this work, we tend to have 4 people. We would have 2 people on the launch and the recovery, and then 2 people on the flight operations. And you can see the takeoff of one of these vehicles and the kind of environment in which we're flying when we're doing it. We tend to push the platforms themselves to the limit. And you can see here at takeoff. Sorry. You can see here at takeoff. With the lithium-ion battery setup that we've got, and it tends to be the takeoff that's a limiting factor because we're already at 4,000 feet and it tends to be quite hot there, so the performance of the vehicle comes into play as well. So the question is, how do we target the plumes? So this particular picture, which is the first one that I showed you, is taken from one of those particular aircraft. In this case, it's heading towards the plume. The thing about the plume is you don't know it's going to erupt as you take off. You know it's going to erupt at some point, but you don't know exactly when it's going to erupt. So the protocol that we got into was to take off, to place ourselves relative to the summit, somewhere that we could watch the activity on the volcano and we could react to it when it did actually erupt. Which takes you on to the interesting question of, you know, what level of autonomy do you want these vehicles to be operating at? So it's, as you know, relatively simple to have it fly a series of waypoints, and you can see that's what it's doing here. We're flying a series of waypoints in this zigzag as we go up. There's several reasons for doing that. One is you don't want to climb up in the lee of the volcano because we are downwind of the volcano summit. So you want to stay away from the air that's just down from the summit because it can be very difficult to climb up into. Second thing is you want to operate your vehicle at the most efficient climb rate. So you want to use the minimal energy possible that is required to get to the top. You can actually see on the way back, spiraling down. Obviously, when you're coming back down again, that doesn't apply. And you can actually glide all the way from the top, all the way to the bottom here over 10,000 feet and 8 kilometers. You can also probably see on this figure here, there's this kind of pink line here that is being flown in the fly-by-wire mode. If you're familiar with the plane software, then we're flying at a fly-by-wire mode, which allows our PhD student, Ben Schellenberg, on the right hand here, to actually fly remotely and target the plumes that we're interested in. So this is a fairly early flight where we're flying up automatically, and then we get to the point where we want to fly through the plume, and Ben takes over and flies it in a fly-by-wire mode in order to collect the sample, and then we automate the recovery. So in this case, pilot workload requires some level of autopilot involvement. Automation is desirable there, and that's where we're heading with this work, and one of the main aims to fully automate this process. The reason being is the more that we can automate it, the more we can hand it over to other people so they can also use the same techniques. So how do we know if we're in the plume or not? Visually, we can detect it, and you can run algorithms that can look for plume and can visually detect it. It's also good to know when you're actually in it. And here is some data involving temperature and humidity. This section in the middle of the flight is actually when we're within the plume. And you can see there are changes in temperature and humidity there that are quite characteristic of being in the plume. The other thing that's interesting is that you get, this is flight data off a flight, you tend to get a drop in the throttle required because there tends to be rising air in these plumes. So the vehicle is naturally trying to rise, but you're trying to maintain altitude. You also tend to get increased level of turbulence when you're within the plume. And so we've come up, there's a paper that we published where we were looking at the combination of the temperature, humidity, and also the flight data on board in real time to detect confidently when we're in the plume or not. And the idea behind this is that if we can do the detection automatically, we can start to do the flight planning automatically as well. This is a video of I think this is the first time that we actually flew through a plume. We were quite cautious in the early stages of the plumes that we were flying through. And you'll see you lose slight visibility. It becomes a little bit more turbulent. The aircraft is correcting. At this point, we would have the stubs open and we'd be collecting samples. And then we close them as we came out the other side. So that's a fairly light plume, and we're just glancing the edge of it and capturing samples. And one of the great things, again, about working in a team, we're working with people. In this particular case, we had Matt Watson there, the volcanologist, who gives us a lot of real-time feedback about what we're looking at, because we've got real-time video coming down to us, and we can actually target in real time which part of the plume we'd like to sample. So one of the lessons coming out of this is there is really tight collaboration between the pilot, and we do still have a pilot in this case, and we have ground control that is studying where the vehicle is. We've got a ground control station here, but also we've developed our own what we refer to as widgets, which tell us specific information about what we're looking at in the plume and gives us data in the flight compared to previous flights in particular. So when you're doing something, you're doing repeatedly, you get better at doing it. And so when you're comparing your data to a previous flight, you can make a decision very quickly about what you need to do. So we have ground control working closely with the pilot and obviously with the drone that is flying. So the sort of next stage in this is this was quite a neat point where we actually created ourselves a rally point near to the top of Fuego. So we climb up towards it. And then these pink sections here, each one of these is passing through another plume. So we're going between the automatic waypoint following to Ben taking control of it, and flying through the plumes themselves for the purposes of the ash collection. And if you do this repeatedly, and we did it repeatedly for about 10 days in 2019, building up experience with the aircraft, building up experience with what we were trying to sample, then you find generally you get better at doing it. The resolution isn't particularly good on these, but we did 39 flights over about a 10-day period. Actually, that should be 2019 because these were carried out 2019. We looked at 2 different battery chemistries, but you can see generally the flight time that we're having in the air increases, and the time above the summit increases as well, in particular with the different battery chemistries that we've got there. So this was one of those flights in 2019. The size of that plume, it's probably up to about 1 kilometer in height at its greatest extent. And you'll see as we fly through the bottom of this, this is around about, oh, this is at 18,000 feet, which was the upper of the limit of the flight envelope that we had. And you can see us passing through the bottom of that plume. You might, if your screens are good and you're getting the bandwidth, you might even see some of the ash passing down over the vehicle as we fly through it, and we're taking these samples. So by the time we got to doing this flight, we were quite happy to fly through some really quite turbulent plumes, and we collected a large number of samples. What was also interesting is that this particular plume, we got samples from within the plume itself, but we also had samples of the ash falling out over ourselves and over the village that was just downwind of us. So we could look at what we collected within the plume in conjunction with what was collected as it fell out. So as we move towards fully autonomous flights, this was a flight that we did in that campaign as well. And what we did here, it doesn't look particularly interesting, but it's quite exciting because as we took off, this was the target altitude, the vehicle took off, and as it translated across this leg here, it optimized the route to the top. So the previous flight plans you've seen were ones that we came up and we generated by hand. In this case, this particular trajectory is generated on the fly after the vehicle is taken off. The reason for doing this is it takes us closer to where we want to be with the autonomy side. And the next challenge that Matters has given us is to capture the same plume, both proximal and distal to the vent. So we're going to tie together the automatic detection of the plume, automatic detection of being inside the plume, together with real-time flight planning whilst we're up there, in order to target the same plume in 2 different positions. And this helps them understand how quickly the ash is falling out and the composition of the plume, both close to the vent and further away as well. So that's where we're going with that particular work. So I'm going to move on to 2 other applications of aerorobotics in volcanology that we've been involved with. This work here was carried out by Dr. Kieran Wood, one of the team here in the flight lab at Bristol. And this is using imagery from drones or aerorobots to look at plume volume calculations. So this was from a single flight, taking a series of images of the plume. This is obviously a plume coming out. This is a gas plume as opposed to the ash-rich one that we were flying in earlier. So it's a different type of volcano. But if you have imagery, ideally from multiple vehicles at the same time, but it can be of a plume that is relatively constant in terms of the temporal variation with the same vehicle, you can process the data and you can work out an exact volume of the plume. So we did this first with static cameras from the ground, all aimed at Volcan Fuego, and worked out the volume of this particular plume. And then we carried it out with imagery that we took in flight from the vehicle. And so having the plume from different places, Kieran has written some brilliant software which calculates the volume of the plume and allows you to understand the size of it, the cross-sectional area, and actually with certain cameras at different wavelengths you can understand the composition of it as well. So that's the target of this work, and there's a couple of papers on there again if you're interested in extracting the volume and understanding the composition of what's in there. And then the last application I'm going to talk about, which will take me from Central America to Papua New Guinea, is in-plume gas measurements. So this was carried out again by Kieran Wood from our group here at Bristol, and in conjunction with Dr. Emma Liu, who I mentioned earlier from UCL. And you'll see two early examples of this on the left-hand side, and this was testing over Bucaya. Actually, that's Fuego there, but this was Bucaya, both of these in Guatemala, with real-time gas measurements. And this is a slightly larger vehicle with a different set of sensors, but doing the same things. It's measuring SO2, H2S, and CO2. So based on this experience and the results that we got from there, we were invited to take part in a project that was led by Dr. Liu, which was called Aerial Observations of Volcanic Emissions Using Unmanned Aerial Systems. And this was funded by the Deep Carbon Observatory. And it was looking at this particular volcano, Manam, that is in Papua New Guinea. It is an island volcano off the shores of Papua New Guinea, relatively inaccessible. And actually, it's been studied, but relatively less so than other volcanoes. So you'll see a list of people that are involved at the top there. And again, I refer you back to my previous comment. One of the brilliant things about this is working with people. And in this case, it was people from all over the world, from University of New Mexico, Michigan Tech, Costa Rica, Papua New Guinea themselves, and the local volcanic observatory, Palermo, Germany, and where we've got Chalmers University, and also ourselves here in Bristol and Cambridge University. So this team, it's called above, went out and studied Manam volcano. And the challenges of operating these vehicles. On the top right, you can see the largest flat area on Manam. And that was both our takeoff site and our recovery site. So that gives you an idea of some of the challenges and of where we were working. And then we're also flying over a highly active plume, and you can see that in the top left-hand side of this. High exit velocity of the plume there, and relatively high and inaccessible from anywhere else on the island. We had an absolutely brilliant time there. The local villages were absolutely brilliant. They welcomed us. You can see my colleague Jim Freer taking part in the welcome ceremony that we had there. And it was brilliant working with them and finding out more about the volcano and the risk and the threat that they live with daily there. So we flew over the plume, and you can see here that you can see the crater itself, magma at the bottom. This was taken from one of our vehicles from a downwards facing camera we've got there. And we were flying through the gaseous plume here, which starts, and we flew directly through that. And we got the highest measurements I've ever seen of certain gases within that particular plume. Highly energetic, high exit velocity, interesting airspace in which to operate. And we've got the main crater and the plume itself that we were targeting. And again, there's publications if you're interested in doing that. So really to wrap up, I've got just a slide here which I'll go through relatively quickly, but if I've learned a few things from doing overseas field trials and becoming involved in these challenges, these are the things that I've taken away. Manage the risk, safety is paramount. Safety is at the heart of everything that we do, and we work closely with the local air authorities to get the permissions and to maintain our safety when we're out there. Do your homework, collaborate closely with local people and institutions, along with the team. Working with local people and institutions is one of the great benefits of doing this work, which I love doing. Multiple deployments, you never get your best results on the first deployment, just as your simulation never works perfectly the first time you run it on your computer. So if you can afford it, have multiple deployments and include what I call a recce trip, which is a trip to go and see the challenges without the pressures of actually operating. Do the paperwork and preparation before you go. Travel lightly and take everything with you. Don't send it separately because that can be a problem. Team working is the benefit, and look for complementary skill sets. Have a clear test plan, but be prepared to be flexible, and definitely don't invite the cameras on early trips, which is what we did once, and that was a mistake because they capture all the frustrations of what we do. But those are the main takeaways that I've taken from this. Our future work. The areas of research that we're particularly looking at are in autonomy and the human-machine interface, and that goes as far as control and real-time planning. And I'm really interested in tying in the sensors very closely between detection, identification, and route planning. So we're going to be looking closely at that. Physical interactions with the environment, where we actually deploy sensors, pick them up again, and that leads us on to multiple robots, including aerial, but also ground robots, to study particular targets of interest. So that really takes me to the end, Jose, which I think is around about the 42-minute mark. I've got some pretty pictures here to run. If anybody's got any questions, I'd be delighted to answer them.
Thank you, Tom. A brilliant talk, very nice, quite interesting. It would be very, very nice to have you here to fly over our Popocatépetl volcano, definitely. So please.
I'd love to come.
Yeah, definitely. You're welcome, more than welcome. So please, members of the public, if somebody in the audience wants to make a question, you can write it down in the chat. You can send it to me and I will read it to Tom.
That would be great. Thank you.
So in the meantime, I want to stay with this point that you made about multiple robots. And certainly you could use ground robots and combine with fixed wing drones. But I was just wondering, what are your thoughts on using maybe not quadcopters, but octocopters? So basically all these multi-rotor vehicles. Is it possible? Are they reusable in this scenario?
Okay, so most of what I've shown you has been fixed wing flying from the observatory. Just go on to the last slide here. But it is possible to fly multi-rotors across Macatenango at Fuego, and the distance is 2.6 kilometers and the height gain is about 200 meters. But you're flying round about 3,800 meters above sea level. So the performance drops off a little bit there. The distances are okay, but the flight times are reduced. What we're going to be doing in January, because we're going back there in January, we'll be starting to deploy sensors and to recover them as well. So because the multi-rotors can't remain in place for long, there is a lot of scope for deployable sensors, and those include ground robots that can move as well in these environments, because there is benefit to moving. Altitudes that we're looking at here. Beyond that, multi-rotors do struggle, so some kind of mixed mode vehicle or fixed wing is probably more appropriate higher up.
Okay, because I was wondering whether we had this idea of how do you call it, like a mothership. So you have like a large airplane, and then you take on board tiny robots like multi-rotors, because obviously if you want to take a multi-rotor from the ground to the top of the volcano, maybe you will run out of battery. But if you just drop them, and maybe multi-rotors are, they could be more stable on hovering. So I was just wondering whether that would be something useful.
Definitely. Both in this volcanology work and also we were talking earlier, Jose, about the conservation work. I think having a larger vehicle that can deploy over tens or hundreds of kilometers that can take smaller ones and deploy them and recover them, absolutely. I think there's a lot of applications in those.
Okay, we got some questions. So there is a question saying, asking, was it difficult to get flight authorizations?
We've done it in multiple countries, and some countries are more difficult than others. It can take some time. I'm approaching the question of flight authorizations. The more you go back to a place, the more they understand what you're trying to do and the better case you have. So establishing a longer term connection, which is what we've done with DJAC in Guatemala, they've been fantastic. So they understand how we operate, we understand their requirements, and we work with them. The other thing that is good is having quite a good track record. And you've seen images from Guatemala, Montserrat, Chile, Papua New Guinea, Italy. You know, there's a large number of countries you've flown in, and being able to show that you can do it safely in those countries helps with making the case and a good safety case to the air authorities. But it can take time. It shouldn't be overlooked because actually, at the end of the day, you want to be safe. We've only ever lost one drone, by the way. There's probably another question in there somewhere. We did lose one in Papua New Guinea. That plume coming out is highly energetic, and we hit it on a particularly energetic day. So we have lost one drone, but it was intentional to fly into the plume. But it's good to have a safety record, good to talk to people, and good to really plan what you're going to do.
So when you apply for the permissions to fly over, are you required to get a license, or because is there any international organization giving you these type of licenses? I mean, apart from the license for flying, of course, but that you are authorized or you have the credentials to know what you are doing with volcanoes. Is there something like that?
There's nothing internationally, but obviously we have missions with the CAA here in the UK, which we put forward and say, we have these missions in the UK and this is how we operate and this is the safety case. But every country tends to vary in terms of what they need and also what they can grant you. So it's really working with every air authority and their requirements. So the ones in Italy are very different, for example, to the ones in Chile. So everyone at the moment needs something different. But the starting point for us is, what is your safety case? How are you going to work when you're out there? We are insured, by the way. We're insured worldwide for drone operations. So that's a key thing as well. And also here are some publications and a previous track record of what we've done. And that sort of opens the conversation, and then we see what locally they need in terms of meeting it.
Great. So there is another question. Which is the minimum aircraft weight to fly around the volcano?
If you want to go and take some good imagery, then DJI Mavic 2 does a beautiful job from the Catanango. So whatever the mass is of a Mavic 2 or Mavic 3 now. In terms of fixed wing, you probably wouldn't get up there for any meaningful time with anything less than about 4 kilos. The vehicle that we're designing at the moment will take off at 16 kilos. And the reason for doing that is we want to carry larger payloads, and we want more performance in terms of the flight envelope out of the vehicle. So for our purposes, between 4 kilos and 16 kilos is what we're looking at currently. I haven't seen a justification myself for going larger than 20 kilos at the moment, because also as you increase the aircraft mass, the risks involved with that vehicle increase. Yeah. So that's the range that we're looking at the moment.
Okay, thank you, Tom. Another question: did you control surfaces or motors? Did your control surfaces or motors be damaged by ashes? Okay.
Good question. Okay, multi-rotors, if you fly them through volcanic gaseous plumes, they destroy them very quickly. So they're very acidic. And so the lifetime of a multi-rotor drone in a gaseous plume is really quite low. In terms of a fixed wing, you'll notice on the X8s there, it has a pusher configuration. We've had the vehicle come down completely covered in ash, and the motor doesn't worry about it at all, because it's placed behind the fuselage, so it tends to be in relatively clean air. Bearing in mind also that probably the maximum number of flight hours you put on any vehicle is probably less than 100. So we're flying really low flight hours. And if we notice a problem, we replace them. We have not lost a vehicle in flight because of ash. And we're very careful. We approach things progressively as we go through.
Okay, great. So talking about, or coming back to this point of the multiple drones, because when you show this reconstruction of the ash cloud, which I think is quite nice. So how many do you think you will need to get the better data? So how many drones?
The plan in January is 6. So okay. that plume from 6 different viewpoints will give us a really good reconstruction, I think. The quick answer is the more the better, but we think somewhere between 4 and 6 gives you the benefit of having multiple drones out there. But so 6 would be my starting point.
Okay, but then how many pilots do you need?
That's an interesting question as well. So, in terms of getting permission to fly, who is responsible for each vehicle? It is the pilot at the end of the day to do that. So the kind of flights we're talking about doing with these vehicles are fully automatic. So there can be intervention from a pilot, but it's not necessarily needed. So the question is, can you present a safety case that allows one pilot to look after multiple drones? Or do you need one pilot per drone? The answer for January is we will have 6 people there who can all fly drones. So we'll have one pilot per drone. But the long-term answer is definitely multiple drones, single pilot operation, and to be able to establish the systems and the safety cases to allow you to do that. But it's being done, as we know, with some of the aerial displays anyway. The aerial displays of drones, so people are doing that. But it is part again of the safety case that you make to the local air authority.
Yeah, definitely, and because then you're talking about potentially a swarm of drones, and then you have all these challenges in robotics, right? Like you want to avoid them to collide with each other. You want them to cover the surface in a smart way. So then, yeah, you have to implement all these robotics techniques, right?
Absolutely, and down to our first flights will be pre-planned, but you want them to be able to respond to what's going on in the environment in real time. So that's where I want to go with this.
Great. So, and another question, apart from, well, you got quite a lot of knowledge on how to do this with the volcanoes. I don't know how many researchers can be as specialized as you are with this application. Is there any other application where you could take all this knowledge and apply it to another type of problem?
Absolutely. In terms of operating in harsh and difficult environments. The other thing that's really nice about, as we're looking here on the screen of Frego and the environment around Frego, is that we have the airspace open to us, because actually not many manned aircraft are going to want to fly this close to an active volcano. So when I was there a few weeks ago, I noticed in the program for later on today, you've got wind measurement using drones. So that's something we're really interested in and working with the Met Office on. So we were doing some high altitude flights with radio sondes, and we did them close to the volcano here. So applying it to meteorological applications, applying it to different environments. And I mentioned conservation is a really interesting one for us. We talked about previously radiation mapping in Chernobyl. That's something that we've done, which has been really neat. So anywhere that you have a harsh and challenging environment, pollution monitoring, visual inspection of offshore oil rigs and those kind of things, all can learn lessons from what we've done here, and we're looking at different environments so we can apply what we've learned. So it's great working with the scientists, but I think drawing some of this out and applying it commercially is also really an interesting area I'd like to go to.
Definitely. Well, with that, Tom, thank you very much indeed. We are very happy, well, the organizers and I personally on behalf of the conference, we thank you for this very nice presentation. I don't know if you want to say a last message to our audience.
I'd just like to thank you all for your attention, and thank you again, Jose, for inviting me. IMAV is a fantastic conference, and it's a great pleasure to be part of it. So thank you very much.
Thank you, Tom, and thank you, everybody. So with this, we finish this keynote presentation. I didn't introduce myself at the beginning. My name is Jose Martinez Carranza. I am the general chair of this conference, and I had the privilege to introduce Tom, our keynote presenter. And now we have some minutes left. So the next session chair, Cesar Martinez Torres, Dr. Cesar Martinez Torres.
Being grown using ultra-wideband. This is a research project that I did at the MAP Lab of the TU Delft Faculty of Aerospace, and my supervisors and colleagues were Maciej Karasek, Diana Olenik, and Guido de Korn. And first of all, I would also like to thank the IMAV and the organizers for the opportunity to share my research with all of you. Having said this, let's start. So first, the context of the assignment was that this project was meant to be a collaboration between the TU Delft Faculty of Aerospace and a startup called Flapper Drones, which is currently focusing on the research and development of flapping wing drones, as well as some potential commercial applications. Currently, they are working on an accurate indoor positioning system for automating flight routines in Flapper drones. And the company so far had explored the possibility of integrating ultra-wideband as a positioning system. The assignment in general, the objective that we defined was to design a controller able to perform full autonomous flights of a flapping wing drone by using ultra-wideband technology as source for position feedback. And then the main research question that we proposed was how can the ultra-wideband technology be used to design a feasible and accurate position control system for a flapping wing drone. Then from this main question, we had 4 sub-questions, each of them addressing the main elements of a control loop. So essentially, what would be the mathematical model for our system, what kind of controller we will require, the measurement error that we can expect from ultra-wideband, which is the feedback in our control loop. And lastly, how should the output of the actuators be modified to get a more stable response? Since this involves automating flight routines in a flapping wing drone, there are many main challenges, which I guess most of you must be familiarized with them. For instance, that the aerodynamic models of flapping wing drones are typically too complex for a real flight implementation. We also have to deal with inaccuracies of positioning systems that are mostly due to noisy measurements. And of course, we have the physical limitations that are inherent to flapping wing drones, mostly in terms of power consumption, the payload, and also the mechanical vibrations. The previous development was basically 2 tools, which we had already available from the beginning. So first, there is a working prototype from Flapper Drones, which is basically called the Flapper, as I will refer to it from now on. And in order to get the controller, we would work with the open source software developed by Bitcraze for their most popular drone, which is the Crazyflie 2.1. So essentially what we did was to take the firmware for the Crazy Fly and make the required adaptations so that it would work with the flapper. If any of you have before worked with Bitcrazy software, then you might be familiarized with this control loop, which is the default controller that you have. Essentially, this is a triple cascaded PID controller, where our outermost loop is in charge of position and velocity. Then we have an attitude controller, and the innermost loop is an attitude rate controller. The sensors were essentially two. For one side, we have the ultra-wideband system, as I mentioned. This ultra-wideband was working with a TDOA algorithm for the position estimation. And together, we also had our IMU. And then we had the state estimator module, which is, of course, required to feedback the measurements to both the position, velocity loops, and also the attitude loop. And here we have an important difference, because the original implementation for the Crazy Fly, for the state estimator, uses extended Kalman filter, which is in charge of of estimating the values of these three controllers. But then when we made the adaptation at the beginning for the flapper, we would see that the extended Kalman filter would only work with the position and velocity, but that the attitude estimation, this one we would have to make it using a complementary filter. And then the problem here is that the complementary filter only relies on IMU data, so it's not taking into account the ultra-wideband system. And besides, there is no integration between the estimates that we were getting from the complementary filter to feedback the extended Kalman filter. So these were some problems that we had at the beginning. Then after this, our experimental setup was essentially to build the ultra-wideband grid, which consists of 8 anchors, and each of them were located at the corners of a room. The sensor, the ultra-wideband sensor that we use, you can see it here, is the Decawave DWM1000. And all our flight experiments were carried out at the flight arena from the TU Delft Faculty of Aerospace. This flight arena has also integrated another positioning system, which is a high precision OptiTrack system. So basically we had 2 position systems available. The first one is the ultra-wideband, which is the one that is sending the measurements directly to the flapper to perform all the onboard estimation. And we also had the measurements from the OptiTrack. Here it's important to mention that there was no integration of the system to the flapper. It was only used to provide a reference to know how accurate the measurements were from the ultra-wideband when compared to the OptiTrack. Then we did our first trials, and here you can see, well, what were the behavior that we were getting for position in X, Y, and Z, the same for velocity, and the same for the attitude in pitch, roll, and yaw. So as I said at the beginning, because we were using this complementary filter instead of the fully integration of the extended Kalman filter, we had many of these errors. So for instance, this unsteady takeoff at the beginning that you can see, a lot of oscillations and overshoots. We had some high commanded velocities. And here you can see a constant pitch error, but then afterwards we determined that it was actually due to some errors in the trimming of the initial values. But well, anyway, this was what I'm trying to show here is that, of course, the initial performance was not the optimal. And how to improve the performance, we approached with 3 different ideas, which were to define an attitude velocity model to account for the drag compensation. Because as you can see here in our initial performance, the value that we get from the velocity never reaches the commanded desired value. And we determined that this was most likely due to a drag that was affecting the response. The second solution was to model a voltage-dependent variable-based thrust for the height control, and also to look to the ground effects that might be influencing the performance of the drone. So now let's see each of these solutions individually. For the case of the pitch and roll, well, for the case of the drag compensation, we did some pitch roll velocity experiments. So essentially, we will only give a step input in pitch and roll at a certain angle, and then we would like to see what was our transient response in the corresponding velocity. And then from here, we would eventually reach a steady state value. Then the idea was that from this velocity data, we could model it following an exponential regression model. So the typical form of this equation, as you know, is this one here. And then what you observe here is that in blue, we have the data, the raw data that we get for the transient response in velocity. Then we only take certain values for the regression, which are the ones in orange. And then with this information, we are able to apply the regression model to see how it approaches to the real data. This was only to corroborate that we could actually extrapolate the final steady state values using the initial data. But then, of course, at the end, we would use all of the data for the regression. This is just an example to show that the regression model and the actual data would match with a certain error. And then for each steady state velocity, we map it against the angles. And then we will see that the plots that we obtained were also possible to model them with an exponential regression model. And we do this 2 times, first with the flapper, but we also take some data from previous experiments done with the Delphi. The Delphi is essentially another kind of flapping wing drone, but with a smaller dimensions. The flapper is a bit bigger. The purpose of trying this with 2 different models was just to check that the regression model could be applied regardless of the drone that we were working on. And then the plots were for pitch and also for roll. And then later on with this, we could actually get some way to model a feed forward value that could compensate the drag that we were observing in our transient response. Then secondly, for the voltage thrust model, the second approach was just to do some hovering experiments and keep the drone flying until we get out of battery. The battery ran out of voltage. And the purpose of this was to find the base thrust that was required for each to a certain value of the battery voltage. As most of you may know already, of course, when the voltage of the battery decreases, then the thrust base shall increase. So we have this kind of inverse proportion relationship. And then from here, we would implement this model of the voltage to the controller so that we would see a variable base thrust. And we implemented with the P and PI controllers. And also we check it against a constant base thrust. So summarizing, we would do 4 kinds of experiments with P and PI controllers, and also with the constant base thrust, but also with our regression model for a variable base thrust. And then we would try it under 5 different linear motions, which are simply in X, Y, Z, and also in XZ, so climbing up forward and sideways, also climbing up. Here I just show you some of the plots we had, so for the sake of simplicity. What you can see is that indeed the PIs will of course get a better performance than just the P controllers. This happens whether the height of the drone is the same, it is constant, or whether we have a change in the height. The influence of the variable or constant base thrust was simply that the standard deviation would be lower. So that means that our response would be more consistent, even though the battery voltage would begin to drop. And thirdly, we analyzed the ground effects. Essentially, again, it was to perform some hovering experiments at different heights, to use a voltage thrust relationship from the previous experiment so that we could correct for the real thrust. And then we would retrieve a thrust ratio. So as you know, ground effects appear when the thrust ratio is higher or smaller than 1. When it is 1, it means that we are getting same thrust that we are applying. And this was the equation that we used to model the behavior. And at the end, we find out that the ground effects were really not significant when we were flying above 0.5 meters of height. From 0.5 meters below, the ratio would drop to 0.92. So that means that most probably when reaching heights below that, then we would have some influence of the ground effects. But in this case, the heights of less than 0.5 were only occurring when we were either taking off or landing. So they really didn't affect the full flight. Here, after we implemented these changes, well, here you can see a comparison of performance. Once we were able to integrate the full Kalman filter against when we were using the complementary filter, then yeah, indeed, all the standard errors that we get for X, Y, and Z are smaller with the Kalman filter than the ones that we had with the complementary. So in average, we had errors between 11 and 13 centimeters, and then with the Kalman filter, they dropped to around 8 and 9. Here you can have a more qualitative idea. So here was the flight. We're working only with the complementary filter. So you can see that it should land here at the intersection of the tapes. Sorry about that. And here it should, when we use the Kalman filter, it reaches more easily the intersection. So there we could demonstrate that indeed the Kalman filter was giving a good performance. And then lastly, we perform a validation where we define two versions of the controller. So one with the modifications, that is the modified version, and a raw version that is without any of the solutions that I just mentioned. Then we would analyze the transient response to step inputs of different amplitudes. So step inputs were of value 1 and 2. And then we test them in X, Y, and Z. And then we would measure both the position and velocity. You can see that in all cases, the modified version, the one with the changes, yields a better performance than the one we had with the raw version. And basically here, you can also observe the plots. So indeed, during rise time, which is below 1 second, the error of the modified version, which is the blue one, is always smaller than the one from the raw version. And also another interesting thing to observe is that most peaks of the modified version are above around 0.4 meters, while the ones for the raw version, they always go beyond 0.6. So yeah, in essence, we were getting a better results with the modified version. Lastly, the conclusions that we had are that the mean absolute error decreased approximately 1.5 times when using the modified version. We observed that our attitude velocity model was valid not only for the flapper, but also for the Delphi. So this means that this exponential model that we apply can be used for different kinds of flapping wing drones as long as there is experimental data available. Then the voltage dependent thrust yields some more consistent performance. This is something that we observe in the standard deviation error, which it was always smaller when using the variable thrust than the one we obtained with the constant thrust. And lastly, that the ground effects do not have a big influence as long as the drone flies above 0.5 meters from the ground. And lastly, we identified that there might be 3 interesting topics for future work. So the first one is that the drag compensation I mentioned was only applied for the controller, but maybe it could also be included for the estimation procedure. And then for this, we could use the IMU data. A second thing is that maybe a more robust implementation of the ultra wideband can get a better accuracy. As I mentioned, we were working with the TDOA algorithm for the position estimation, but so far we find that there are now more robust and sophisticated algorithms that could be used. And lastly, that in this case, we were working with the IMU, but as you know, because of the mechanical vibrations, the IMU measurements tend to be noisy. So maybe if we incorporate other sensor sources that are unaffected by mechanical vibrations, we might get better results. Some examples of these sensors would be a magnetometer and barometer. And yeah, that would be it. Thank you. And if you have any question, please feel free to ask.
Thanks, Guillermo. Anyone have a question? I think we have time for 1 or 2 questions. Well, I have a question, Guillermo. In your first slides, when you show the diagram of your controller, your cascade PID controllers,
Sure.
I think altitude, yeah, they have different rate frequencies.
Yeah.
Could you explain the reason they have different frequencies?
Yeah, sure. So basically, for the attitude rate, we are working with a higher frequency because the accelerometers deliver measurements at a quite fast rate. So we need to get the data, sample the data faster. But then for the position and velocity, the dynamics of the system are slower. So yeah, there is a sampling frequency that is smaller. But in this case, the way we can compensate for it was just that we would average, let's say 5 samples, and then that average is the one that is sent to the position and velocity.
Okay, so you use average to synchronize the controllers, right?
Yeah, precisely.
Okay, okay, thank you. Thank you, Guillermo. I think we're in time now. So paper number 23, I think is Joe, right?
Yeah.
Yeah.
Hi.
Hi, Joe.
So let me share my screen.
Yep. Please go ahead.
Okay, this should be visible, I think. Oh, is this the wrong screen? Wait a minute.
Don't worry.
So are you seeing the full screen of my PowerPoint presentation or the presenter view?
We are seeing now your onboard time optimal control tiny quad for tiny quadcopters.
Yeah. Okay, perfect. All right, so let me start. I apologize in advance if I speak very fast because I have some trouble meeting the 15-minute requirement. So if something is not clear, ask me the questions at the end. So hi everybody, my name is Jelle Westenberger and I will be presenting our work called Onboard Time Optimal Control for Tiny Quadcopters. This research was performed also at the MAV lab in collaboration with Christophe de Wachte and Professor Guido de Kroon. And we propose a controller that is a lightweight model predictive controller that approximates some time optimal principles. So for those unfamiliar with optimal control, it is basically the field of mathematics where you try to find a series of control inputs that optimize a certain cost function with respect to some value. So you can, for instance, optimize for smoothness or for spent energy. But in our case, because we are focusing on drone racing, we are most interested in optimizing for minimum time. So in general, solving these problems is done by satisfying either the Hamilton-Jacobi-Bellman equation or satisfying the conditions for optimality, as stated by Pontryaghin's minimum principle. And there are generally numerical solvers like nonlinear programming or dynamic programming methods that solve these. But these are quite computationally expensive. So you have the choice to calculate your optimal trajectory beforehand, which has the disadvantage that you cannot incorporate any environmental changes on the go. Or the other choice is you calculate your trajectory on the go, and if you incorporate your quadcopter model, you look at model predictive control with the big advantage that this is very dynamic, so you can react to changing objects in the environment. But the downside is that you need quite a powerful computational module to be able to do this. A more recent approach that has been done in research is using machine learning to, for instance, train neural networks to approximate some reference trajectories that are calculated by the traditional methods, and then execute these on the fly. The downside of this method is that it's very data intensive and time consuming to train these neural networks. So summarizing some downsides of the current method is that it's too computationally expensive to easily implement it on board a quadcopter. In terms of machine learning, it is often too data intensive to quickly implement it. And there are a few efficient trajectory generation methods that can be executed on board. For instance, the minimum snap trajectory generation by Mellinger and Kumar is one of the most popular papers in this field. But just like this example, it is not time optimal, but it is actually optimizing for a certain smoothness of the trajectory. So here comes our proposed controller, which we call the Bang Bang controller. We call this the Bang Bang controller because it is based on the assumption that for constrained time optimal problems, the solution often has a Bang Bang shape. This means that the input values are either maximum, 0, or minimum. And the big advantage of assuming this is that the control problem only reduces to a problem where you only need to find these timestamps at which it will switch. So you don't need to worry about the values of the control inputs anymore. So our approach is to plan a bang-bang maneuver between two targets and then optimize the time at which you switch from accelerating to braking based on path predictions. So we try to reach the target with a certain desired velocity, and the switching time is optimized until the velocity error at this target is small. So the attitude angles, pitch or roll, are always saturated, but only one of the two, because if we want to extend this problem to two directions, we have to look at a what we call a critical direction and a non-critical direction. And what this is can be shown in this example. So here we say that this longitudinal direction is the critical direction. So we plan a bang-bang motion in this direction, which is in this case performed by planning bang-bang in the pitch angle. And we have a so-called minimum effort angle in a non-critical direction, which is the roll in this example. That is where we calculate a constant angle value, so such that this position is reached at the same time as the longitudinal component of the position. So you don't waste any power on the lateral. You don't waste more power than needed on the lateral direction, while you maximize the power needed for the critical direction. So the control parameters in this problem are the switching time and the non-critical angle, and we calculate this based on path predictions. So as computational efficiency is our main node to take away, we need to look at a simple path prediction formulation, which should be analytically an analytical model. So we find this by reducing the dynamical model of the quadcopter quite a bit. So we assume linear drag, we assume constant thrust and therefore also constant altitude. And of course, the attitude angles are assumed to be constant during the path prediction. Summarizing, we can derive some differential equations, which calculate the position and speed at any time. And by combining this, we can use a bisection scheme to iteratively optimize the switching time or the non-critical angle. So when we start in the critical direction, we have here a path prediction, which consists of a acceleration phase and a braking phase. And we assume that during this each phase, the attitude is constant and also that the thrust is constant. And during the transition, we assume that the angle, for instance, the pitch angle, changes instantaneously. Then we use a simple bisection scheme that starts with an initial guess of switching time that iterates on the switching time until your velocity error at the target is within a certain precision. When we have a nice value, then we start with the non-critical direction, and this uses the same bisection scheme, but instead of switching time, we now change the roll angle, or the non-critical angle, I should say, such that the lateral or the non-critical position error is minimized at the same time as the estimated time of arrival that we have gotten from the first optimization loop. And finally, also while we're braking, we also optimize the angle with which we are braking to incorporate any premature braking because of imprecisions. So when we summarize the computational effort that needs to be done for this optimization loop, we can say that for the switch time, we only need 4 function evaluations of these 2 functions per iteration. And on average, we need about 10 iterations to reach a certain desired precision of the switching time. Same goes for the non-critical angle, but then you only need 2 function evaluation. And if you sum this, then we can say that during the acceleration phase, we only need 60 total evaluations to reach a desired switching time and non-critical angle. And during the braking phase, only 40, which is not a lot at all. So we can say it's fast enough for a real-time model predictive controller that can run on board a quadcopter. This we first tested in simulation. We compare our method to some reference trajectories done by that look like a minimum time trajectory, and also by a more traditional high gain PID controller. So the minimum time trajectory is calculated with the popular iClocks toolbox, which uses direct collocation to calculate this trajectory. We performed some simulations, first in a straight flight. Here the blue line is the minimum time solution. You can clearly see there's a change in altitude as well. And the purple line, I hope it's visible on screen, it is straight because we assume constant altitude. And yeah, despite it being very fast, it also shows some overshoot at the target. Similarly, in a cornet flight, it overshoots its first target and also overshoots its final target. So we need to worry about why this is happening. In order to identify this, we look at the prediction accuracy. So, and for that, we can look at our estimated time of arrival during simulation. Because if you have perfect prediction from the start, you can assume that the estimated time of arrival should remain constant. But as you can see in these plots, they actually increase during the rotations. And this makes sense because we assumed instantaneous rotation switches. So at the switching time, it would switch from the braking or acceleration angle to the braking angle like immediately. But in reality, it will of course cost a little time or take some time for the drone to rotate. So in essence, we will always brake too late, and we need to compensate for this somehow. How we do that, I will explain in a few slides. Because first, we have performed some flight experiments at the same lab that Guillermo also did this experiment from the previous presentation, which is the Cyberzoo. Our drone that we use is the consumer-grade quadcopter called paired BUAP, and it has been modified to run the custom Paparazzi UAV autopilot software. So here's a brief overview of our control pipeline. In addition to the optical tracking system of our lab, we also use a complementary filter to improve our position and velocity estimations. Then we have a PID controller for the altitude control, our bang controller, of course, and a high gain PID controller that takes a more traditional approach to control. The bang controller and the PID controller spit out create roll and pitch commands, and these are given to the inner loops, which are based on INDI. So here's an example of what happens during a maneuver. On the left plot, you see the prediction of the critical direction, where the blue line is the actually flown path, and the green line is the acceleration prediction, and red is the braking prediction. The right plot shows the non-critical direction prediction, and yeah, in a perfect case, the roll command should remain constant, but because of inaccuracies, we can see that it will change more quickly as we get closer to our target. So as I mentioned before, we need to compensate for our transition losses. So for the fact that it takes some time to rotate from one angle to the other. Also with taking computational efficiency in mind, we know that it is difficult to model. So we have defined some rotation losses, which is the time it takes to rotate from one angle to the other, and also the position and speed that we lose during this rotation. If we can approximate this somehow and augment our path prediction with these values, we can hopefully convert to a better switching time. So we approximate these losses with a simple linear regression model. We obtained this model by simply measuring our time, speed, and velocity in flight during the rotation. And then we have created 3 models for the forward, backward, and sideways motions, because the quadcopter is not aerodynamically identical in these directions. So here are some we have performed some experiments where we start from rest and end in rest, and tested in the combination of longitudinal and lateral flights. We compare our bang-bang controller to the bang-bang controller with the compensation system enabled, and also we compare to a traditional high-gain PID controller. So in this video, we compare the bang-bang controllers with compensation and without compensation. These videos are overlaid on top of each other. The green drone has compensation enabled and the red one hasn't. And you can clearly see that in both cases there is some overshoot still, but the compensation system is definitely doing some good in terms of overshoot. Similarly, if we compare the bang-bang controller without compensation to a PID controller, we see quite some overshoot for the bang-bang controller, and the PID controller barely has any overshoot. This is better visibly in these box plots. These are box plots of each maneuver that we have performed. The BBC label stands for bang-bang control with compensation enabled, and you can clearly see in each plot that shows the overshoot that it is much better than the bang-bang without compensation, but it doesn't come close to or it doesn't reach the same level of overshoot as the PID. And this is because the PID controller is in essence a controller that is either critically or even over-damped in position control, because it is proportional to your, because it will follow a desired speed, and that speed is proportional to your position error, and it has been tuned in such a way that it won't overshoot. But this also means that in theory, it should brake too early, and that is the place and time where the bang-bang controller should perform better than the PID controller if we manage to calculate the switching time more precisely. Also, because we designed this controller with drone racing in mind, we need to look at a scenario that more closely resembles drone racing. So we've come up with this experiment where we have 4 waypoints at which we don't intend to stop, but perform a continuous flight. We keep our heading constant because that's unfortunately one of the requirements of the bang-bang controller, and we automatically switch the direction which we consider to be critical based on the largest position error. So this is a video where we can see what happens for both controllers. So the green one is bang-bang with compensation, and the red one is the PID controller. We can see that both controllers manage to complete at least one circle, but the PID controller oscillates and also loses stability at the end. And this plot shows it more clearly. On the left the bang-bang, on the right the PID, and we can see also when we look at the distance to each waypoint on the right plot here that the bang-bang controller flies through the waypoints much more closely than the PID controller, and we can see that the PID controller will overshoot its first target and then also start to oscillate in order to compensate for this overshoot. Which ends up that the PID controller is less stable than the bang-bang controller, but also it takes longer to complete a circle. So the bang-bang controller is here about a second faster on average. So the reason that this happens, or that we see this difference in behavior, is because the bang-bang controller is able to prioritize thrust to one direction. Because we have bang-bang maneuver in one direction and a minimum effort approach in the lateral direction, while the PID controller uses the same gain values for both pitch and roll. And if we, this equation basically approximates how much thrust we need during the flight. And if both pitch and roll are high values, these terms become very small, so the required thrust is much higher. This means, this we can also see in this video. The red one is the PID. And you can see that right at the start of this maneuver that the PID controller moves to the right immediately, even though its largest position error is in the longitudinal direction. And the bang-bang controller flies more in a straight line to its intended target, which is more power efficient and makes it more stable. So the PID controller is always closer to its maximum thrust capability, therefore less stable, and therefore also slower than our proposed controller. So this brings me to our conclusion. We have proposed a lightweight bang-bang model predictive controller which unfortunately still comes short in step responses, but in theory should beat the PID controller in the braking phase. It outperforms the PID controller in continuous flight because it can give different priorities to different axes. And also it is about 7.5% faster on average in completing circles. It is easy to implement because we require only minimal knowledge of the quadcopter's dynamics. We only need mass and drag, and we need to estimate transition losses. Also, because it's very computational efficient, it can be implemented on many drones, also with more limited computational resources than the BUAP. On the BUAP, it was able to run at 512 Hertz without even saturating the processor unit. And compared to the PID controller, it has the advantage that we don't need any gain tuning or gain scheduling. It can fly many different maneuvers from the go without any tuning. And under some strict conditions, we can say that we approximate time optimality under the conditions that our angles remain constant, such as the heading and the pitch and roll during the acceleration phase. Also, we need to assume constant thrust, so we cannot incorporate any maneuvers that require a difference in altitude. And finally, one downside is that we need to predefine the desired velocity at the target, which means that our solution is not globally time optimal for the entire trajectory. So finally, my future recommendations. We have set our pitch, roll, and thrust limits conservatively. In future work, this should be made adaptive so we can fly close to the limit of the quadcopter. We can explore a different way of calculating bang-bang maneuvers. So instead of roll and pitch, we can look at the thrust factor and point it towards our target or away from the target, and then translate that back to roll and pitch angles. Yeah, as I mentioned before, we had to do some effort or make some effort to estimate our transition losses, but this can also be done online, for instance, with recursive least squares method. And finally, we have praised our computational efficiency, but not actually analyze it in a proper way. So we need to analyze, for instance, how much floating point operations we need in order to quantify our computational effort. Well, this brings me to the end. So if there are any questions, I'm happy to answer them.
Thank you, Joel. I don't know if someone had a question. We are in time now. Yes, I have a question. How do you ensure that you have the best PID gain selection?
Yeah, well, we used one set of gains for the PID controller to keep the comparison fair, and we tuned these for the maneuver where we have a longitudinal and a lateral offset. So yeah, it has been tuned by only looking at the maneuver where we fly forward and straight at forward and laterally at the same time. And that has been tuned by trial and error, basically, so that we can get the best performance for that maneuver, and then we use the same values for each other maneuver as well.
Okay, thank you. And finally, one final question. Have you compared your approach with a non-linear controller, for example, saturated PID?
No, I'm afraid not. We only compared it to the theoretical time optimal solution and the high gain PID controller that I mentioned before.
Okay, thank you for your presentation, Joel. I think Romain,
are you
ready?
Yes, I am ready. Good morning, everybody. Can you hear me?
Yeah, we can hear you.
Okay.
Please go ahead.
I can share my screen. Can everybody see my screen?
Yeah, we are able to see the screen.
Okay. Sorry. So good morning and good night to everybody. I'm Romain Jean, a PhD student in ISA Super in France in aerodynamic department, and my co-director of thesis is Dr. Jean-Philippe Contamine from ENAC, and my director is Professor Jean-Marc Mosqueta from ISA Super as well. So I'm about to present you the modification I've made on a fast simulation model for control law design and benchmark of high aspect ratio UAVs. So during my work, I'm using the software called AI Swing developed by Professor Magdalena at MIT during the 80s. and it's mainly used to simulate the behavior of flexible aircraft, but specifically high aspect ratio aircraft. And it used many different theoretical results that we have decided to study at ISA Super-Héros. And we have chose this software because of the different function it proposed, such as model analysis, frequency analysis, and specifically temporal simulations. As it uses different theoretical backgrounds, it kind of imposed a workspace that I just recalled here on the right. So we have to use high aspect ratio wings, and it allows small to high deflection regarding the flexibility. And you can study aircraft until max 0.7, that because it uses compressibility transform space to recover an incompressible space. You can simulate up to 20 beams, 20 different beams, so that you can consider as lifting surface. And you can also implement up to 12 engines, 20 flaps, and you can put as well 20 sensors that can monitor up to 40 different physical variables. Just to give you an overview of, for example, the aerodynamic loads computation under I-swing and the different theoretical background used. It uses an unsteady lifting line theory using the vector form of unsteady Kutov-Joukowski theorem. And it uses also the influence function of different objects on the aircraft, such as vortices and volume influence, as well as jet swirl, which is very interesting for investigating the effect of the propellers over fuselage or wings. And separation and stall are modeled to predict lift and drag up to pre-stall, and we do not recommend post-stall behavior study. And regarding drag, it uses three-component friction, pressure drag, and a post-stall contribution. Regarding fuselage, it uses an unsteady form of the slender body theory that I would not recall here because it's a bit out of the scope of this presentation. Just to give you a motivating example, we are looking at ISA Super-Héros to show that I-swing is still accurate for modern application. So I'm just giving you some simulation we have made regarding experimental data for tandem aircraft, which are a bit studied today, especially in China, for example. And we have managed to show that I-swing is accurate to predict lift and drag for a certain range of angle of attack. So I-swing is still accurate for modern application, but regarding the control part, you can only implement multi-input, multi-output PID controllers. So the idea was to modify I-swing so that you can implement a bunch of modern control law strategies. But as I-swing is not a MATLAB black box, but a compiled program, we had to look into the program because the source code is accessible, and modify it so that we can implement our control law strategies. So this scheme represents the actual or the current control law strategies that you could implement under I-swing. And basically Q and U are different state vector, and Q are the censored physical variable. So the problem statement is that we have to modify the solver, which is used for different type of simulations, such as model analysis, frequency analysis, and temporal analysis. And it uses always the same strategy, which is a Newtonian descent multi-order algorithm. So I think it's very efficient. I forgot to mention that because you can run simulation in almost real time, and it's efficient because of the way how the solver has been implemented. And so we have to respect a certain pattern so that the internal solver use very efficient matrix inversion algorithm to solve the temporal iteration very quickly. So the idea was to implement the control law that I have summarized here in a nonlinear form first, and then to invert the extended Jacobian matrices that you need for every problem, such as time marching or modal analysis. So first of all, the idea was to modify the source code to implement the nonlinear control law, but the main drawbacks was that every time you want to change a nonlinear control law, you have to go into the source code and compile again iSwing. So the idea was to propose a linear control pattern that kind of recover as much as possible the linear control strategies that are used nowadays, and use it as a black box with MATLAB. So you don't have to go into the source code anymore, and you just have to give the different matrices of each block that I will present. So the pattern is made of different blocks. So the first one was to add actuator dynamics because they are not simulated in the iSwing, and the saturation blocks. As well, we did the same for sensors blocks, and we had controller block dynamic and also anti-wind up system for the people who wants to investigate stability problem for saturation problems. Note that every block can be scheduled by any variable from the Q vector, so up to 40 different variables. They are following a multivariable input-output linear pattern, and we have implemented, three different methods for addressing gains. So nearest neighbors and bilinear interpolation that was already used with the previous controller strategy in iSwing, and the bipolynomial strategies. So I just made a tab to kind of summarize the different linear controller strategies that you can implement as long as they are following a linear state state vector form. So, and of course you can still implement linear controller strategy, but you will have to change and modify the source code, which is not very practical yet. So finally, I'm just going to give you some quick example as illustration. So the first one is very easy. It's just to show the difference between the current controller strategies and the previous one, where we have implemented just first order dynamic for the engine with a 3-second time response, and we have set 2 different saturation levels for 0 thrust level and 7 Newton thrust, 7 Newton saturation level. And we can see that now the engines behave more like a real physical system. So that was the first example. Then just to show why we have decided to modify the internal controller strategies. Just a simple example, the previous work has shown that it is possible to harvest energy and gain altitude with the adapted deflection of the elevator of any UAVs flying through a gust. And this example just shows the effect of an actuator dynamic on the closed loop system. Sorry. So we thought that it was more realistic to simulate the behavior of an aircraft with the actuator dynamic to see the real effect on control law strategy in closed loop. And the last example is just a motivation example for energy harvesting and the limits of basic control law strategies. So we have implemented a function under iSwing that can simulate Van Kalmar 3D spatiotemporal gust environment. And we have shown that for the same control law strategy where we were gaining altitude through time, here the objective of the control law strategy is not fulfilled anymore, and we have some kind of random behavior through the time, and so it motivates the needs of investigating new and modern control law strategy regarding energy harvesting. So those are just 3 examples to illustrate kind of the toolbox we propose here. So sorry, I have been a bit quick, so thank you very much for your attention, and I will answer your question.
Thank you, Romain, for your presentation. Anyone have a question? We have a question. So, where is the simulation carried out? MATLAB on, and which is the numerical method used?
Sorry, can you just repeat?
Where is the simulation carried out? MATLAB for a question, and which is the numerical method used?
For the simulation, we have used the software, so iSwing, but you can output the data and plot them on MATLAB. So it's a MATLAB plot, but this is the software simulation. And regarding the numerical method, is it regarding the solver or the overall theoretical background of iSwing?
Cesar, I think it's about they want to find out about the numerical method that you use in your work.
Yeah, the question, well, the person who made the question says, yes, for example, RK4.
Okay, so regarding the numerical methods, so a same solver is used for 3 different strategies. So modal analysis and frequency analysis, where you study the steady or unsteady Jacobian of the residual system of equations. And for time marching computation, you are using a Newton descent algorithm to reach the residual perturbed state residual equation to 0. So the overall problem is to study the Jacobian matrix and invert it. So the numerical method, it's a Newton descent algorithm. And regarding the inversion of the matrix, it's used a Gaussian block matrix elimination algorithm. And inside this algorithm, you can identify different patterns that can solve the problem quickly. And specifically, this state vector, I won't explain you what those variables are, but this state vector, it's a differential equation, follow a specific pattern that you can use to really get the solver quicker.
Okay, thank you. Anyone another question? Okay, I think we have no more questions. So thank you, Romain.
Thank you very much.
We are just in time for the next session. The next session called applications. I don't know if presenters are already in the room. Paper number 4, paper number 13, and paper number 22. I saw paper number 4 and 22. Gauthier. Can you hear me?
Yes, we can.
Yes, I can unmute.
Okay. And paper number 13, I think it's not already on the room, right? Okay, so we have 2 minutes for the next presentation. I don't know if you have some announcements.
Just a reminder that we will have our second panel session of the conference, and that will happen after this session finishes. So yeah, don't miss that session. Thank you.
Okay, thank you, Jose. Okay, so we could start, Gauthier, with the first with your first presentation. Go ahead.
Okay, let me. Can you see my screen?
Yes, we are able to see your screen.
Okay, so hello to everyone. My name is Gauthier Attenberger. I'm a researcher and assistant professor at INAC, the French Civil Aviation University. So my presentation today is a field report of a project aiming at deploying a fleet of drones for cloud exploration. And this project is called NEFELAE. This is actually an atmospheric science project. And the goal is to understand the evolution of the evolution of clouds during their lifetime. And to do that, we need to deploy several drones and to have adaptive exploration to be more efficient. And this was a collaboration between INAC, LAS CNRS, they are specialists in robotics, and the Météo France, the research center for meteorology in France. The technical objectives of the project regarding the UAV side was to be able to track cumulus type clouds during their lifetime. And actually this life cycle is quite short, it's about 20 to 30 minutes. And because the winds can carry the clouds, we have to be able to track them up to 6 to 10 meters per second of average wind. Then we need to collect data, and the scientists are actually looking at very specific locations of the clouds. It's not a question of just going through it without really knowing where we are. They want to get especially data from the border, so the place where you have an exchange between the open air and the inner the inside of the clouds. And they are also interested with the center where you have the maximum intensity of the internal phenomenon. So to do that, we need to navigate using the sensor data in real time. And finally, we want to fly several UAVs at the same time in order to get synchronized data from different locations and especially from different altitudes in order to measure some airflow inside the clouds, which means that we need to coordinate the flights. So all the details of the trajectory that we have been using have already been published, and you can go through these previous publications. Yeah, so my presentation here is to is about the field campaign, because the NFLIA started in 2017, and the end goal is to actually deploy in a real life mission. And we had several preparation flights, especially in France, in a place called Lannemezan. And it's very difficult to deploy the complete system and test the sensors in real conditions, just because it's difficult to get flight authorizations to go high enough. So let's say 1,500 meters at least to get the clouds. It's not possible to get a large flight area, so we can follow them for a long time. And everything is quite difficult to test beforehand, but we had these opportunities to test some parts of the systems, and also finding the correct locations to perform the real scientific flight campaign is also difficult. And several places have been tried or envisioned to do that. And finally, we had the opportunity to join an international meteorological campaign that held on the Barbados Islands end of January 2020. So just before lockdown, we have been really lucky to join this campaign that involves piloted aircrafts, drones, boats, unmanned boats as well, and so on. So after this introduction, I will present the preparation and logistics to do this Barbados mission, and then the field campaign itself. Okay, the first thing to prepare the mission was to find the correct locations on the islands where to fly. It's a rather small island, and there is at the south international airport. So we have to find a place which is far enough from the airport so that we don't intersect the aircrafts during their initial and final approach. And also we know that there is this cloud observatory here on the islands, but the only possible place where we have enough space and far enough from the airport is at the north of the island here at Morgan Lewis, which is this place here with a large field where we can operate. And it's directly in front of the sea. So actually the wind is coming from the oceans, pushing the clouds towards the island. And the general flight plan idea was to fly within this triangular shape, which is around 14 kilometers long. So fly to the end of the flight zone, wait there to get some, to find some clouds to follow, and come back with them towards the island. And the flight ceiling was between 1,000 and 2,000 meters above sea level, depending on the flight authorizations. In terms of logistics, we had at least 10 people involved during this mission with researchers, engineers, and PhD students. It lasted for 4 weeks, not all the people together at the same time, but still a lot of people to manage. And also we had to send all the equipments, which planes, ground equipments, laptops, tools, batteries, at least 2 months in advance with a cargo ship. And it was actually even quite difficult to get them out of customs. And for the operating center, we had 3 containers for storage and operations. Now the deployment strategy. We had assign 5 roles to the people. So the first one is the atmospheric scientist. His role is to provide the high mission goals. So what are we looking for? And also to look at the real-time data coming from the planes to assess their quality and to tell if the signal is an actual cloud and if it is worthy to start the tracking of the cloud. The second person is the map maker. So is a computer scientist here in the middle. Is monitoring the real-time cartography system. So based on the data measured in real time by the planes, we are constructing a map of the clouds on the ground, and we are using this to monitor the system and also to give some information to the aircraft to improve their autonomous navigation. The next operator is the UAV operator itself. So here on the right, his goal is to monitor the flights of the UAVs, mostly for the safety of the operations, of course, during the takeoff and landing, reaching the end of the flight zone. And when the tracking starts, he gives the control to the atmospheric scientist and map maker to do the automatic tracking. Then we have the safety pilot outside handling the critical phases of landing and takeoff. And we have only one for all the aircraft flying at the moments. And finally, we have a flight director, which is doing the general coordination between all the other operators, but also with the other teams operating on the zone, because we were 3 teams operating drones from the same fields, and also be in contact with the air traffic controllers of the Barbades. And on the right here, you can see the general software architecture of the system with the autopilots. So everything is handled on board by the autopilots. The second processor is only for getting the data and sending it to the autopilot, which is doing the automatic adaptive navigation and stabilization, communication, etc. And on the ground, you have here the UAV operator and the atmospheric scientist and map maker looking at the mapping system. So the airframe that we have been using are commercial foam aircraft, X-06 Skywalker, about 2 kilograms, 1 hour of flights, takeoff from the bungee. The main reason to use those type of aircraft is that they are very robust and easy to repair. During the project, we have been developing custom design aircraft with tremendous characteristics, like more than 2 hours of flights and very fast flying. But it was way too fragile to be used in actual real flight campaign. And yeah, one of the important things that we have learned is that we should prefer the robustness and ease of repair when in the choice of UAV. The most important sensor for the navigation is that we call the cloud sensor. It's actually LEDs emitting lights that are what to say? Sorry, that are monitored by this small sensor here, and it's measuring the retrodiffusion of particles of the atmosphere, and it's able to tell first if we are inside or outside the cloud, and also to reconstruct some physical characteristics of the atmosphere. And of course, we have long-range modems and the paparazzi UAV systems to fly the planes. So the general flight plans operation, it's a 5-step classical takeoff, then going to the initial climb to reach the target altitude. We know from the ground observations the roof altitude of the cloud base. so we have to be slightly above that. Then we reach the end of the flight zone, and when we had the chance to find clouds with the cloud sensor, we start the tracking, and this strange shape here is the automatic adaptive tracking of the clouds until we reach the end of the flight zone or the coast, and then we have the landing. So to summarize the flights, we had up to 48 flights, 22 with 2 UAVs at the same time. Lots of hours of data recorded. And among the flights, we have 23 only for calibration and validation of the flight pattern strategy and sensor calibration as well. And so 25 for measurement flights, and only 18 finally that have been able to track the clouds for at least 2 minutes. And yeah, and not so many crashes. We have only lost 1 plane, or actually we have broken 1 plane beyond repair. Okay, so what have we learned from this flight campaign? The first thing is that operating in a foreign country, it makes every little thing a little bit more difficult, or way too difficult. If you cannot afford to forget anything from your lab, because you will not find locally in a short time. We have spent a lot of time to do calibration flights, and one of the reasons is because flight testing is really difficult. Flying inside the clouds and following them needs a very large airspace, and it's very difficult whenever you are. Also, the initial plan was to fly up to 5 UAVs, but we have been only able to fly 2 at the same time, or actually we have intended a flight with 3, but one of the plane had to land shortly after takeoff for technical issues. And that's one of the reasons. The number of available sensors, planes, hardware failures that we couldn't repair during the mission. And also the operator and safety pilot workload, because there were only 1 safety pilot and 1 operator. It becomes exponential when you increase the number of UAVs. And important points, searching for clouds with only local perception is really inefficient, and we need to get better systems to guide the aircraft to the initial points to find the clouds. And when we lose a cloud, we also need a better recovery mechanisms to get back to the tracking. So the future improvements, the first one is to, as I said, improve the robustness of the adaptive flight patterns, especially with a recovery mechanism. And these have been implemented and tested successfully in France, but with only hybrid simulations, which means that we have a real aircraft flying, but simulated clouds, and the flight altitude can be very low, close to the ground. The second point is that we should use vision-based systems to detect the clouds. Meteo France is working on a camera system called All Sky, a network of camera actually, to try to measure the initial position of the cloud, and we have to feed that to the system to find the cloud faster, and don't lose time waiting for them. And finally, we have to integrate a task planning and collision avoidance system so that we can lower the UAV operator workload. And this is also ongoing work at LAS. So as a conclusion, I would say that atmospheric science is a very exciting field for a UAV system. It deals with very complex and unknown dynamic environments. And UAVs are very good at that, and they are good assets, but we still need a lot of works to make it very more practical to use and to deploy, especially as a fleet. It stays very complex at that time. So even if we have not met all the scientific and technical goals that we have set at the beginning, I think that the collected data are extremely valuable and good, and we have already pushed the state of the art a bit further, and the scientific results out of those flights are being published, or they will be very soon. They are under review. Thank you, and I will answer your questions.
Thank you, Gautier, for your presentation. Anyone have a question? Yeah, I have two questions. The first one is, which kind of autopilots have you used in your UAVs?
The autopilot is, so it's using the Paparazzi UAV system for the software, and for the hardware, it's a custom design, or maybe I missed it. Okay, no, sorry, it's not written. It's a custom design that we have developed at INAC. This board is called Apogee. It's a simple microcontroller-based autopilot. It's very similar to the Pixel autopilots. It's using STM32F4. So everything is running on all the navigation, and the autonomous adaptive navigation is running on the microcontroller.
Okay, thank you, Gautier. And the second question is, have you implemented an algorithm of synchronization between the two UAVs used in the mission?
Not yet. So there is no direct automatic synchronization, but when we were flying the two UAVs at the same time, so when one of the UAVs found a cloud, we manually sense the second one at the same clouds and at different altitudes, so we can do some kind of layers of clouds. And yeah, the one of the future works is to automate this with high-level goals and a task planning system. So you can say, okay, I want to follow a cloud while measuring the airflow. So the system knows that it needs two available aircraft, and they can send it to the correct place. So in this example, you have only one tracking, and the second one had to go back before actually reaching the same cloud, because we are only interested by following the same cloud by multiple UAVs, not several clouds apart.
Okay, thank you, Gautier. I think presenter, thank you, Gautier. I think the presenter for the paper number 13 is not connected. I didn't find it. Uyuki, do you see him or see her? No. Could you please play the video, Uyuki, in order to maintain the schedule? Thank you.
Hello, good morning, and welcome to a presentation about my research project developing a modular tool to simulate regeneration power potential using orographic wind hovering UAVs, which is quite a title, but we'll break it down for you in a short bit. I'm Vidas Fossi. This is my research project I'm doing to acquire my master's degree, for my thesis project from acquiring my master's degree in aerospace engineering from Delft University of Technology. It's a joint project in the Netherlands drone working group, which I'll explain to you shortly. And also in our group are Sanyu Huang, PhD supervisor, and my supervisor as well, Bart Lenes, also from the MAV lab from the Delft University of Technology. I'm really thrilled for you to be able to show you the progress I made in our project today. So first, a short outline of today's presentation. So first, some general information about the Never-Landing Drone project, where this project fits into. I'm going to tell you some of the previous research that was important, or sort of that was the stepping stone for our research itself. Some of the research gaps we identified, then the main show our research itself, and then some test results of our test setup of our regen drivetrain as well. And at the end, there also will be some time for some questions. So let's get started. So the Never-Landing Drone project, it's basically a working group where we try to find innovative ways to have a UAV stay in the air indefinitely, ideally through harvesting energy from the environment in some way, shape, or form. Of course, there are already very old methods that you could use, like regular soaring, as you can see in the picture below, with regular sailplane. With this method, of course, one of the issues is that you're really dependent on the current conditions. So either you need a hill close by where you can get ridge lift, and also, of course, a sufficient strong wind that's aligned properly with the ridge itself, or a good thermal. But the problem is, you're really dependent on the conditions. And if, for instance, you want to stay at a certain physical location itself, it's also really difficult while harvesting energy. Another more modern method is to basically use solar panels on the plane. It also has it has the advantage, of course, as long as you have sun. You're able to do that anywhere, doesn't matter which altitude you're circling at. But of course, as soon as if it's like a really cloudy day, or at night, for instance, you're not able to take advantage of that. It's also really tricky with the charging system involved as well, which brings us to another example, for instance, inductive charging systems. They have the advantage if at every site you install one of them, you can just have, if the power transfer is big enough, you can just have a drone hovering there indefinitely, and then even also charging the battery while doing another mission in the end when it's fully charged. The problem is you have to install one of these systems at every location you want to charge your drone, as well as that you have to have quite quite some infrastructure in place to also support the there's high losses basically between those two coils. So you need quite a big power source as well to be able to do this. One novel method that I wanted to research was trying to see if we could combine so-called regen soaring and wind hovering techniques to be able to hover in the updraft of, for example, a hill or another large object like a ship, for instance, and then use the regenerative drivetrain to be able to use the excess atmospheric energy in that updraft to recharge the battery while you're still hovering in that same location. But in order for that to happen, I'll first explain some of the two basic concepts that that concept combines, mainly so regen soaring and then later wind hovering. So with regen soaring or regenerative soaring full out, you use it's pretty much like a standard for sailplane catered electric UAV, for instance, but you're also able to use the propeller as a wind turbine, so not only as a propeller, and your motor as a generator. And what this does is you're able to, if you engage it as a turbine, be able to apply extra drag to capture more atmospheric energy, and then store that energy through, if you have the correct power control unit that is able to reverse the power flow, then you can use that to recharge your battery and store electrical energy. So for regen soaring, you can, for instance, you can just do normal ridge soaring as well, of course, but then instead of storing your energy in the form of potential energy in the form of altitude. You can also first recharge your battery and then still go on to a higher altitude, or even use it to, if you, for instance, for some reason your mission requires you to stay at a certain altitude, you can still harvest energy, otherwise it will drain also. Now the regen soaring concept is actually already quite old. It was first proposed by Paul McCready, quite a famous name in the soaring world, in 1998. But he mainly just touched upon the possibility of this concept and the techniques required, and technologies also that would need to be further developed. But in 1998, it wasn't really feasible yet with the battery technology available at the time to be able to construct a feasible prototype. Then further research was done more recently by Philip Barnes. He actually designed a concept regenerative soaring plane, as you can see the picture on the right hand side below. And what really got from his paper was that the trade-offs required for trying to design your drivetrain for both propelling your UAV as well as or sailplane, as well as trying to do the regenerative part, which actually proves to be quite tricky. Unfortunately, he didn't really perform any experiments. It stayed with just a concept plane design. There is, however, one commercial use of this technology already, which is the Pistrel Alpha Electro. Pistrel is a Slovenian company. It makes this really nice light training aircraft. I think it was actually the first electric aircraft to be certified. And it uses a specially designed wind prop, which is a propeller that they designed to be able to be both efficient in the propelling and the wind turbine regime as well. And it basically uses its special drivetrain to regen aero brake during the descent phase. And it has a special power control unit, or PCU. It is able to maximize the regen power by having a feed vector where it monitors the RPM and tries to be in the perfect range where it can harvest the most amount of energy. And they use it mainly because this aircraft is designed to do circuit training. And if they can do steeper descents, and then while in the meantime also recharging battery bit, they can, with the same battery capacity available, they can actually do more training circuits once for students, which is really beneficial. Then the second concept we need to touch upon is wind hovering. So wind hovering, in contrast to regenerative soaring, wind hovering, you actually try to stay in the same physical location. So you're trying to find a point in an updraft of a wind field where, with the current conditions, and of course, if your UAV is aerodynamic enough, it is able to orient itself in such a way that it can just not climb, not descend, but actually hover in that same location. And the main paper that's already explored this concept was emulating avian orographic soaring with a small autonomous glider back in 2015. Actually managed to do some successful hovering experiments in front of a hill, even some very short experiments in a building where they managed to do it for a couple of seconds. And they mainly developed the hovering flight dynamics equations that we used as a basis for our calculations as well. And the concept of the feasible soaring region that you can see in the right-hand corner below, where they try to construct a contour region, or visibly see that, where the updrafts are high enough for a certain UAV to be able to, if the conditions are right, that they could hover in that region somewhere, which was what we also used as a basis for our concept. And then finally, the last piece of the puzzle is region electric drivetrains. What's really interesting is there's already been a lot of research into region electric drivetrains, but mainly into light electric vehicles like e-scooters, e-bikes, and even light electric cars. But what's interesting in these lighter vehicles is that they try to optimize their system, where they use the three-phase inverter for both. They regeneration gene. So they basically cleverly use these components with a different switching algorithm depending on if they want to generate or provide power to the engine, which is of course really good for also using in UAVs because you have less heavy power components required, which saves mass. And they also even use the coils of the motor itself as part of a boost converter to be able to, if the voltage that is regenerated by the engine is not is lower than the battery voltage, they use those coils of the engine itself to boost that voltage up to the battery voltage again, so they're able to recharge it. So it's really optimized control system. But even with this research in place, we still identified some research gaps. So as pointed to earlier, most research doesn't really contain a lot of practical experiments. And the whole the wind hovering concept doesn't seem to be explored yet. So the combination of the wind hovering plus a regenerative drivetrain and the actual and finding efficiency figures of this optimized regen drivetrain, yeah, it's also not really possible. So we set out to our research set out to try to yeah, bridge some of these gaps. So our research mainly focused on the two areas, which was trying to estimate the optimal power regen in a certain wind field. And this, of course, sort of entails two subcategories. You need to do first a wind field estimation around the object to see if it's what the wind fields are, to be able to put them through then your flight dynamics equations for your regen system, determine what the estimated power will actually be that you could be able to regen from it. And then secondly is determining the efficiency of the regen electric drivetrain, the optimized regen electric drivetrain with that combined switching methodology that I pointed to earlier. So first, the estimation of the wind field. There's of course many ways to do it. You can do it with CFD analysis tools, but we opted for actually first doing it relatively simply with a potential flow simulation. The nice benefit of this is that you can easily alter the flow conditions and shape, and then have a very light computational tool that is able to give you results already. So it's very quick and easy to alter the conditions. And also in the back of our minds, we're thinking of trying to maybe implement this algorithm later on board as well on UAVs, which also yeah, benefits considerably from having a very low computational footprint. For these potential flow simulations, we also try to include the wind gradient effect. And we did that by using a standard logarithmic boundary layer function that they can use for wind turbines to determine what the wind speed is at a certain height, or yeah, determining what also the power would be from wind turbines at certain heights, which proved to be really useful. And on the bottom right corner, you can see an example of the output from our wind field estimation tool for an oval-sized hill. Of course, developing this altered potential flow diagram, flow program would be pretty useless if we didn't try to clarify it first. So we did actually perform some calculations with the OpenFOAM CFD package with the simple foam solver. And for some select cases, we actually did simulate it through the CFD package. And the nice thing is we also made our tool compatible, so later our tool is able to calculate the actual power contours. It's also compatible with the outputs from the CFD package. So if you actually take the time to do more complex simulations, like for instance, the field around the hull of a ship, you're also able to import that into the tool to see the contours around those shapes as well. Next, the flight dynamics bit. The wind hovering flight dynamics, wind hovering regenerative flight dynamics were based upon that avian soaring paper that I pointed to earlier. An important addition, of course, is the drag of the turbine, which wasn't there before. But this drag is, of course, variable depending on how much you sort of activate or how much load you draw from the turbine. And we found out that it is you're actually able, if you take the Betz law as a simplification for the maximum amount of power power/drag that the turbine would be able to draw from the wind field. You can express this as a sort of a drag coefficient, which you can set equal to 2/9 of the fraction of your disk area of the turbine versus the surface area of the wing. And with that, we were able to construct a very basic hovering criterion. So if the required combined drag coefficient of your clean aircraft plus the part of that your turbine needs to generate, if that is between either the minimum drag, basically, so it's just of the clean aircraft without turbine activated at all, basically folded, the propeller folded back, or the drag coefficient of the clean aircraft plus the turbine at maximum utilization. If that criterion can be achieved, then you can conclude that the UAV can actually hover in these conditions. This is an example of what it looks like if we put it through our tool. So this is an estimation of the regen power region for a 50 m/s wind field around a hill with a radius of 50 meters. And the more dark red the area is, the higher the power figure. Interesting to see also is the turbine utilization. So we could see that in the previous slide for for example, for these points where, of course, the wind velocity is low, it's very low, even when your turbine is completely, you try to take the max power drop from a turbine because there's not a lot of wind, you get a very low power figure. But more in these regions, you got a higher power figure, and there also you have, so this is sort of the optimum point because you have a relatively high wind speed, and you can have a maximum utilization of your turbine. Then the next thing that we needed to look into is the electric drivetrain efficiency, which turned out to be also quite a hassle because these we couldn't really find out these figures from literature. And we needed to find a way to determine the power available to recharge actually the battery, given your mechanical power that we get from the estimation from our wind field. And this both includes the efficiency of the BLDC as a generator as well as the regen controller. We used a test setup with 2 engines coupled back to back, and for the regenerator controller, we used a commercial VES Eurovesk with a custom STM32 microcontroller that was able to program in a set braking current. This is what it looked like. So we have 2 engines coupled with mechanical shaft coupler. This one, the right-hand engine was driving, the left-hand engine was connected to a torque measuring setup as well. And then the left-hand engine was then connected to the VESC regen controller, which was then able to do the special switching, the switching element algorithm, whereby even if the generated voltage of the motor was lower than the battery voltage, it was able to boost it up using those switching elements and the motor coils as a boost converter, and then convert that to a higher voltage for the battery. And we basically ran this test setup for quite a couple of parameters, and then we ended up with these nice efficiency graphs. So as you can see, it's really dependent on the RPM and the requested mechanical, the available mechanical power. But we were actually quite pleasantly surprised. We were able to get a top efficiency figure of around 70%, which is actually higher than we first expected. And you can also see the details of our test setup on the left-hand corner. So this concludes basically the research at this point. If there are any questions, please let me know, and I'll be happy to answer them. Thank you for listening.
Thank you, Oyuki, for playing the video. So finally, in order to close this session, we return with Gauthier. Are you ready for your next presentation?
Yes. Just a moment.
Thank you. Go ahead.
Okay, can you see my screen?
Yep, we can see your screen.
Okay, so hello again. So, I'm Gauthier Thunberger, a researcher at INAC, the French Civil Aviation University. My presentation here is about the estimation of the wind using quadrotor. So, of course, estimating the wind is very useful, and we have just seen that with the previous presentation and others. And in this paper, the idea is to use the motion of the quadrotor to get a proper estimation of the wind. So first, how to measure the winds from UAV. The obvious idea would be to use a direct wind measurement sensor that could be using ultrasound, pressure, or any other techniques. And but in this case, most of the time the sensors, they are either heavy, expensive, fragile, and you can see on the picture below that it can be difficult to or constraining to install them on a small UAV. But usually the main benefit is that they can observe fast variations, and they are suitable to use for turbulence monitoring, for instance. The second option is to use the trajectory itself, and here we have also lots of solutions that exist for fixed wing when using the ground speed while flying in a circle, for instance, or for multicopters, thanks to the relation between the attitude of the frame and the drag that is generated from the airflow. And well, most of the time it needs some assumptions, especially that the flight speed is constant. It's not the only one, but and the result is that the bandwidth of this kind of techniques is usually lower, and you can only estimate the average winds. And in this presentation, we are going to use this relation between attitude and drag to estimate the average wind, and to show the calibration procedure that we have set. Okay, so first I will explain the general equations, then the calibration procedure, the estimation filter based on the Kalman filter, and the experimental flights. So first, the formulation, we have two equations. The first one gives the relation between the ground speeds, or the derivative of the position, which is equal to the relative airspeed and the wind speed. And this equation is known as the wind triangle. The second equation is well, the Newton's law of motions, where the product of the mass and acceleration, so the derivative of ground speeds, is equal to the weight, drag, and the sum of weight, drag, and thrust in vectorial form. So we already have some assumptions. Well, we only consider rigid bodies, frame and propellers. The inputs of the system are the thrusts from the motor, and they are all along the vertical body axis. So that's really a traditional quadrotor. And the position and orientation, they are measured or estimated without noticeable bias from the fusion of GPS and IMU data. So the general idea is that in the presence of winds, the thrust of the frame, the quadrotor, has to balance the drag and, well, not the acceleration, but the product of the mass and the acceleration from the previous equation. So here, if you have some winds, it creates some drag, and the frame has to bank towards the winds to equilibrate. So what we need to know is the relation between thrust and the bank angle. And also, if we want to solve this problem, we have to measure the weight, which is quite easy, and to estimate drag and thrust. So the thrust model, here it's the thrust projected on the Earth axis, is estimated to be the total thrust, so the sum of all the thrust generated by the motors, rotated thanks to this rotation matrix, which represents the rotation and the orientation of the frame with respect to the Earth frame. And the drag model, it's usually the drag, the friction drag is a function of the square of the airspeed. But it's not only, that would be true without the motors, but since we are using motors, there is also a rotor drag known as the H force, and which is linear with the airspeed at constant rotor speed. And considering the small airspeeds of the quadrotor, it appears that this linear force is dominant in the drag, and we assume that the drag is again proportional to the norm of the airspeed vector, the A. So we have to estimate for both the total thrust and the, to estimate or to calibrate total thrust and the drag coefficient K. So the calibration methodology, well, it's simple in principle, but it's not so easy to in practice. You need some equipment. The idea is to fly at a fixed position so that we eliminate the acceleration terms. And we fly in front of known winds, and we turn in front of these winds. You will see later why. In this case, again, we know that the projection of the thrust on the vertical axis is equal to the weight, and the projection of the thrust on the horizontal plane is the drag. And we are looking for this relation between the alpha equilibrium, so the bank angle, to the drag. So for different wind speeds measured with a reference airspeed sensor, like a hot wire probe, we make at least one full turn, and we record the attitude angle, so phi, theta, and t angle. And we fit the roll and pitch angles with respect to the heading, so the psi angle, with a sinusoidal shape. And so you will get at least 3 parameters, and we are only interested by C1, which is in fact the magnitude of the sinus, the sinusoidal form, and which is equal to the alpha equilibrium that we are looking for. So before looking at the calibration results, let's see the setup. We have built a custom quadrotor with a spherical body so that it eliminates all the asymmetrical drag. So it's independent of the orientation of the quadcopters. And we fly in a flight area equipped with the OptiTrack system. So the position is automatically controlled by the autopilots, and we have the quite good assumptions about the zero acceleration. And we are also using this wind generator here. This is coming from the Windshape company, and it can be seen as an open jet wind tunnel. And we can, of course, measure the reference speed at the location of the rotorcraft. The system is equipped with the paparazzi autopilots, by the way. So the calibration procedure is to make, as I said, one full turn with a stop of 3 seconds every 20 degrees. We can measure from 0 to 10 meters per second, but we have stopped at around 6. And you can see on this plot here on the right that you can fit a proper sinusoidal shape on the data plots here, plotting the roll angle against the psi angle. And the C1 coefficient here can be extracted from this fit based on the MATLAB function for data fitting. And this is for a given reference speed of 6.57. If you do the same procedure for different airspeed and you report all the C1 coefficient for the different reference speed, considering that at 0 you have a 0 bank angle, you can see here that all the dots are well aligned, and the slope, the coefficient of this line, named C alpha, is related to the drag coefficient that we are looking for by multiplying by the weights. And for our aircraft, we have the drag coefficient of 0.23. Now that we have a calibrated model, we need to build the estimation. And for that, we need some extra assumptions. The first one, as we are looking for the average wind speed, is that the wind is constant or slowly varying. So the derivative of VW is equal to 0, which means that the acceleration, the initial acceleration, is also equal to the acceleration in the airframe. Also, the weight is balanced by the TZ, so the vertical thrust in the airframe, which means, again, that we have no vertical acceleration on the vertical axis. And then we can estimate the total thrust based on the mass and the bank angle. Oops, sorry. The estimation is done using a linear Kalman filter. Since we have this linear expression for the drag, we can use this linear Kalman filter here presented in the discrete form. The state vector is the relative airspeed and the wind speed in the earth axis. The measurement vector is the ground speeds measured by the GPS or the motion capture system, and that's it. And you can eventually neglect the second order terms. So the indoor test that we have done in front of the wind shape system, the wind is constant at 3.8 meters per second here. And it's coming from a fake north, let's say. So here we can see that the wind direction is correctly estimated. So it's towards the P, so 180 degrees, blowing towards the south. And the norm is converging slower, around 20 seconds, to get a correct estimate of the norm of the wind speed here at 3.8. We have done also 2 sets of outdoor tests. So we went to the airfields, and with 2 different trajectories. One is a square trajectory here at low altitude, and the second one is a vertical profile up to, I don't remember exactly, but okay, so it's a vertical profile. We have looked at the wind conditions on public data websites, and if you compare the time of the flights and the the recorded data. We expect to have for the square trajectory wind speeds between 0 and 7, so it's not very accurate. And after 10, between 7.5 and 9. And the direction would be from 110 degrees, more or less. So again, the results, I didn't tell before, but this is the state vector elements, and this is reconstructed the norm and directions of the wind. We can see that the estimation of the direction is again fairly good, where we have here the 110 degrees reported in radians, and the norm for the case of the vertical profile. So the vertical, oh, sorry. Here you have the convergence toward the expected wind speed, also around 20 seconds, a bit less. And you can see that the signal on the state vector here, it's much more noisy than the indoor experiments, and that's due to the noise of the GPS much higher than the motion capture system. Yeah. For the square trajectory, of course, the estimation of the airspeed is much different because we are moving horizontally. So we can see with the large variation that the airspeed is of the frame is estimated, and that's the component of the winds are moving much more than in the previous case. And you can see that here if you reconstruct the direction and the intensity of the winds. Okay, it's less accurate and more noisy than the previous case. So it's probably due to bad compensation of the acceleration, but it still provides some acceptable results. So as a conclusion, I would say that this work summarized the methodology for wind estimation and calibration that you can find in the literature. So most of the elements exist in different forms, different models around the literature. So we put that together to get this initial estimation procedure. And a linear Kalman filter is evaluated for indoor and outdoor flights, and it's providing fairly well results. There are still interesting works to do after that. The first thing is to integrate the codes for onboard estimation. This is actually already done, and I'm just waiting for technical constraints to push that into the code base of the paparazzi UAV system. So it will be done soon. And also to compare the indoor calibration using complex equipments with outdoor methods, so based on flight test analysis, and also try to integrate some onboard estimations. And also, and finally, test different geometry, different propeller size and rotation speed, and so on. And that's it. Thank you.
Thank you, Gautier, for your presentation. I think we have time for one question, Jose. All right.
Yes, go ahead, please.
I don't know if someone has a question. Yeah, we have a question. Are there other methods that could be compared with this method you proposed?
So the other methods, they mostly ever differ in the model that they use. So the drag model can be nonlinear, and then they need to use extended Kalman filter, or they use slightly different calibration methodology with free flights, with flight data analysis, or using wind tunnel with force and moments measurement systems. So everybody is making some little different solutions. More or less, they all give the same results, what is not very clear and what I couldn't find, at least in the area of the micro UAVs, is the influence of the body shape. If I remove the ball, the plastic shape in the middle, is it really making a huge impact? And more important, the impact of the motor and propeller size, all of that, the weight of the frame and so on. So probably it exists in the helicopter literature because the H-force is well known there. But for the micro UAVs and for the drag estimation, it's not very clear, and people tend to use fixed coefficient, and that's it. And yeah, and online estimation integrating into the filter is also considered by some people, but you may have a weak observability of the parameter, so it makes things tricky, and you have to provide accelerated flights and so on.
Okay, thank you, Gautier. I think we have no more questions. Thank you. I think we can continue with the panel, right?
Yes, thank you. Thank you, Cesar. So I would ask our panelists to switch on their camera. Gautier is one of them, so he can stay. Let me.
Hello again, Joseph.
How are you, Gautier? Guido, Pascual? Give me a second. I want to announce it on the in the chat. Okay. I think you are seeing my screen.
Yes.
Give me 1 minute, please. Okay, so let's start with this second panel of the conference, of the International Micro-Air Vehicle Conference. I'm very happy to have these former general chairs of the previous IMAVs and also a deputy chair. So thank you to all of you for making the effort to be here and share with the community your experience and what is behind of this of the organization of this event. So I will start by introducing each one of you. I will introduce again Guido. Guido presented yesterday. He delivered his keynote presentation, which I think was a great presentation. If you missed the presentation, you can go to the social networks on Facebook and YouTube. You will find the links of these social networks on the official website, imap2021.inaue.mx. At the bottom, you will find the links, and you can see Guido's talk again. But very briefly, I can say that Guido is a full professor in bio-inspired micro-air vehicles in the Department of Aerospace Engineering at the Delft University of Technology. And Guido has, his team has won several competitions, drone competitions. And if I remember correctly, Guido, you were one of the first, or your team was one of the first teams to compete in the autonomous drone racing when it was organized in 2016 for the first time in the IEEE Aeros conference. And more recently, you won, your team won the Alpha Pilot competition organized by Lockheed Martin and the Drone Racing League. So I think those achievements speak a lot about your work. And of course, I think you will share a bit more of that even if this panel presentation. So we also have the participation of Jean-Marc Mosqueta. He's a professor of, and Guido, of course, was the former chair. He's the former chair of the IMAV 2014, that was held in Delft in the Netherlands in 2014. Also, we have with us Jean-Marc Mosqueta. He is a professor of aerodynamics at FCE-BUAP in Toulouse, France. And he is the director of the Micro Air Vehicle Research Center. Since 2000, he has devoted his research activity to rotary wing and fixed wing drones, including aerodynamics design, energy harvesting techniques, transitioning vehicles, quiet propellers, and recently, Dr. Mosqueta has started the development of an hydrogen-powered fixed-wing UAV for flying over the Atlantic Ocean with low carbon emissions. So thank you, Professor, for being here. And he is the former chair of the IMAV 2017 that was held in Toulouse, France. And next to him, we have Gutierrez Hattenberger, who is the deputy chair in the IMAV 2017. He's an assistant professor at the French Civil Aviation University, INAC, in Toulouse, France. And as a member of the UAV research program, he is working on flight dynamics and control of micro UAVs, modeling and simulation, architecture of embedded systems, trajectory planning, and formation flight. And most of his work is based on the open source UAV systems Paparazzi, for which he is now one of the head developers. He graduated from French National Engineering School of Aeronautical Construction in 2004 and received his PhD degree at the Robotics Department of the Laboratory of Analysis and Architecture of Systems, LARS, CNRS, in Toulouse, for his work on formation flight control and planning of UAVs in 2008. So thank you, Gutierrez, for being here. And yeah, we have been hearing a lot about Paparazzi in the last, yesterday and in the last talks today. And finally, I'm also happy to have with us Pascual Campoy. He is a full professor on automatics at the Universidad Politécnica Madrid, UPM, in Spain, where he lectures on control, machine learning, and computer vision. He has been visiting professor at DCSC department in TU Delft in the Netherlands from 2014 to 2019, and previously visiting professor at the Tongji University in Shanghai, China in 2013, and QUT in Australia in 2011. He received his PhD in automatics and robotics at the Universidad Politécnica Madrid, in 1988, where he previously received his master title in automatics engineering in 1983. He is leading the research group on computer vision and aerial robotics at UPM within the Center of Automatics and Robotics, CAR, whose activities are aimed at increasing the autonomy of the unmanned aerial vehicles by exploiting the powerful sensor of vision using cutting-edge technologies in image processing, control, and artificial intelligence. He has been heading director of over 40 research and development projects, including research and development European projects, national R&D projects, and over 25 technological transfer projects directly contracted with the industry. He's author of around 200 international scientific publications and 9 patents, 3 of them registered internationally. He is awarded in the top, or he has been awarded in the top international UAV competitions, IMAV 12, IMAV 13, IR 14, IMAV 16, and IMAV 17. He is a former chair, he was the general chair of the IMAV 2018, and he coordinated the international team that was awarded 3rd place in the Grand Challenge MB Cirque 2020. So thank you to all of them for being here. I will ask you to, first of all, before we go into questions, to share a bit of your experience with the IMAV that you had to organize. So I will stop sharing my screen just in case you want to share some small presentation or a video. So can we start with you, Guido? So please go ahead.
Sure. Let's start. So I'll share my screen. Now, I'd like you asked us to prepare a little bit. So yeah, so we organized the 2014 IMAV in Delft. TU Delft, if you don't know it, it's the oldest and largest Dutch public technical university. It's quite well ranked, and the picture is actually of the Faculty of Aerospace Engineering, which is also typically quite highly ranked. The TU Delft itself has 26,000 students and 6,000 employees. And it's typically beautiful weather, like on the picture. There's no rain whatsoever. So at TU Delft, at the Faculty of Aerospace Engineering, we have the Micro Air Vehicle Laboratory. It was founded in around 2003, but there were already drone activities before that, actually. I put a few pictures of what we do because we do things like AI for swarming tiny drones, but we also make flapping wing drones that we also make autonomous, drone racing, and there's even a part of the lab that works on slightly larger drones, like the scale goes up from here to there, hybrid drones that can take off and land autonomously on ships. And also the control code for these hybrid drones. And so, we cover many aspects of micro air vehicles in our lab. So we've been involved quite a long time in participating in IMAV competitions. The first Delphi in 2005 was presented at basically one of the first IMAVs. And we also organized it a few times, actually. And the last time was in 2014, and I hope the video will work. I'm not sure you're going to hear the fancy music, though, so let's try that out. Okay, there's no music, but that's okay. And so in 2014, we had this idea to combine outdoor and indoor competitions. And so there was also an outdoor competition and an indoor competition. And here actually we arranged a testing village of the military, where we could fly outdoor, but the missions, if you wanted to get most points, the best thing would be to go from outdoor to indoor and then keep navigating there. This is a team from Singapore, by the way. And and this is a team from Aachen. They have become better and better at guiding that aircraft. And so we see many different teams. The idea was that a map should be made of the village. So you could do that with fixed wings, for example, and then combining images. But there were other elements like landing on a roof, flying into a building, forming a relay, a communication relay. And we had also a company filming the event. So they were flying even higher than the other ones. And so they were also filming the other drones, as you see. Some of which perhaps were falling. So that also happened. This is one of the results. This is a beautiful ground station, paparazzi, I guess. And they needed, there was also a task where they needed to detect numbers live and then tell the ground station what number it was. The videos, by the way, it's only still a minute, but I think it's nice to see. This was 7 years ago, so it's quite long ago yet. And here you see somebody trying to enter the building. So at that time, we did allow also for FPV flying, because there was an FPV entry. But this is fully autonomous flight by the Singapore team, which you are seeing now, and also the landing on the roof. And so, there was a mix of autonomy, which was highly rewarded, of course, but also still some FPV flight going on. So I think that kind of illustrates it well. We had precision landing. So the typical precision landing, right? That you flip around. But it is actually the drone that was used by the company to film everything. And so that was my car. No, I'm kidding. It's a completely destroyed car. Anyway, so that's a video. The competition outcome, National University of Singapore won. Actually, on the old website, it also said what they did. So image stitching, onboard number recognition, autonomous takeoffs. They did a lot of things well. And then a team from Germany, and then ENAC was third in that year. And we had, I think I will get the number soon, but I think we had 13 teams. As keynote speakers, we had Petra Muren from Prox Dynamics. So you may know Prox Dynamics because they make the Black Hornet, this really tiny helicopter. And it has to be said, Petra Muren showed off his first prototypes at IMAV. And people may not know this, but so Abraham Bachrach, who is behind Skydio, he presented his work first at IMAV. And also Ascending Technologies, you know, they started with their products at IMAV, you know, showing the control. And so, yeah, it's really curious who in the audience will be the next huge unicorn or whatever they call it. Okay, Eric Johnson from, he was at that time, he was still at Georgia Tech, but yeah, I put Penn State here because that's where he's now. And he was working with slightly larger helicopters. So the Yamaha RT Max or something. And then Sawyer Fuller was the third keynote speaker. He was at the time at Harvard University, and now he's yeah, a professor at the University of Washington. So at Harvard, he worked on the RoboBee, and that's what he talked about. And then it was still tethered, but one of the things that Sawyer did at the University of Washington is make this one, where yeah, they basically shine a laser on here, and then it can fly untethered. And so yeah, there's also a lot of progress being made there. Okay. Statistics that were asked. So we had 262 participants, 39 scientific articles, and 13 competition teams. And yeah, that's it for me. So I must say the outdoor indoor worked out quite well. How to stop sharing? Will somebody make me stop sharing?
You can go to the bottom of your screen. You should see the.
Oh, here. Sorry. Yeah, yeah.
Okay. Yeah. Thank you, Guido. That was a very nice presentation.
Thank you.
Okay, so let's go now with Professor Jean-Marc, please, if you would like to take the floor.
Actually, Gauthier is going to make our presentations because we basically collaborated on that edition.
Please go ahead.
Okay. Okay, maybe just share my screen.
Yeah, we can see it.
Okay, so IMAV actually was organized at Toulouse by a collaboration between INAC and ISAE Super 3 times. So in 2007, it was even not called IMAV, but MAV only. Then 2013 and 17. I will only give some details about the last 2 editions because it's some more interesting. So for IMAV 13, the main focus at that time was the high level of autonomy, multiple UAV, and also the operability of the system. And we had 2 different scoring systems, and one putting the emphasis on autonomy and one putting the emphasis on the operability of the system, more or less the number of UAV you can fly compared to the number of operators that you need. And also make a focus on the autopilots and aircraft design, so system and frame design. You can see that we had the chance to fly for the outdoor in the actual real airfield, where INAC is operating some training, by the way. And the type of missions task were to do some precision navigation, search, fast track flying, precision landing, so some basic stuff. And for the indoor, going through windows, through obstacles, and again precision dropping and landing. We had 44 submitted papers, 12 kept as a scientific paper, and 19 as technical papers, and around 15 teams for indoor and outdoor all together. what we have seen at that time was quite good use of multiple drones by some teams, and especially the teams from TU Delft. They deployed something like 12 drones with a single operator. They didn't all go to the air or land quite roughly sometimes, but still that was a quite impressive performance. And they won the outdoor competition. And some other teams, and actually the one from Pascual from Madrid, they flew several autonomous drones, air drones too, for the indoor mission, and they won the autonomy mission indoor. At that time, the computer vision was quite limited. So all the teams using vision, it was doing either FPV or feature detection, but of known objects like tags. And yeah, we have seen that with the scoring factors, that the being small was quite important. And for the operation mission, the TU Delft with their Delphi, so very small and light, they also get a very good scoring. For the IMAV 17 edition, the main focus were more or less the same. So always on aircraft efficient and innovative designs. So trying to push the aircraft and system design, because that's more or less what our institutes are specialized. Also try to push the small and light MAVs, because we are doing MAVs. So and again push a little bit further every aspect of autonomy in terms of decision or cooperation and image processing, including the multi-UAV cooperation. The type of mission elements, they were roughly the same, but with some new additions. Here you have some structure and unstructured obstacles, wind fans generating some disturbance and so on. And along the usual competition, we introduced some extra challenges. One was a treasure hunt to push the teams to innovate in terms of sensors. There were one for the formation flights trophy, so demonstrating the best formation flights, and that's also pushing the multi-UAV operation. One was a performance competition where you have to carry a given weight for a minimum of time with the smallest UAV possible. And I honestly don't remember the fourth one. For the conference, a little bit more papers, 63, 26 scientific papers, 15 technical papers. And what we can recall from the competition, so all the teams have pushed the vision-based and indoor navigation autonomy a bit further. So there were teams, including yours, Jose, using SLAM. So not always on board, but still not using extra external known tags. Or one team tried to use the ultra-wideband for localization, for instance. What we have seen is that most of the teams have enjoyed the extra challenges, and this is also a very good attraction for smaller teams, the one that don't have enough people or resources to compete for the podium of the regular competition, but they can still focus, for instance, here on the performance trophy or the Parade trophy. And also it starts to be really complicated to keep the correct balance between autonomy and design. It either goes to the computer science and image processing, AI or whatever, and the not the opposite, but another direction, which is the optimization of the performance, the integration of the autopilot, and so on. Those are two aspects that are really hard to balance in the scoring system to get a fair competition, I would say. And yeah, it was the first time, I think, that we have seen some collaborative flights. So I remember the fourth trophy, which was a collaborative carrying. So it was a wooden frame that has to be carried, that as many drones as possible, considering their size also, evidently, of course. Okay, so that's it for the presentation, but I think I found a small video here. So maybe this one is a bit long, but we can skip the end if needed.
Well, or maybe you would like to comment something additional while we see the video.
Well, actually, it shows how complex it is to prepare a competition, because okay, it's complex to take part of the competition, but preparing it is a huge work. It's more than 1 year of preparation, and you need to accommodate for many aspects. You have to find people long time in advance, and on the day of the competition, students or colleagues to help. Here you have a clever way to get more points in the collaborative carrying. It was not explicitly told that the aircraft has to not touch the frame. So what is not forbidden is authorized, I guess.
Yeah, I remember that.
And okay, so and some teams actually only prepare for the extra challenges, and they put all their effort into that for the carrying. That was the case for RMIT. That was the case for the Moscow Institute. And well, in the case of INAC, we took part to the formation flights contests, not the competition. We were the main judges, so that's not really fair.
Yeah, I remember for that competition, the outdoors competition, there were these two poles.
Yeah,
and
so
like quite far away. Yeah,
you have to do some go and forth to prove your endurance.
Exactly.
Yeah, we always try to keep this endurance aspects so that we don't see only quadcopters, but also some fixed wing, or at least transitioning vehicles. Yeah, something which is really hard to find also for this kind of competition is a place which is large enough so people can fly on a large space and actually use flying wings or aircraft, let's say fixed wing aircraft, and not only quadcopters. This is quite hard to find and to get the authorization. And if it's too big, it's hard for the public to follow the competition. So the balance is not so easy after all. And yeah, in that regard, I would say that the IMAV 14 at TU Delft with the village, the combat village, was one of the best place ever for the IMAV competition, mixing indoor, outdoor, and real life environments. Because if you look at the 13 edition or even the 17, the ground is more or less very flat. and that's not the most realistic flying condition for UAVs. You expect them to fly in mountains, close to the trees, close to the buildings and whatsoever.
Yeah.
So, and such a place is not easy to find.
Yeah, definitely. We found a very nice place here in my city for the IMAV 2020 when we were thinking of running the competitions. But well, unfortunately, we will have to wait. Professor Jean-Marc, before we pass the word to Pascual, would you like to add something?
Yeah, I would like, thank you, Gauthier, and thank you all for the nice presentations. I would like to ask a couple of points. I really agree with Gauthier about the role of those extra challenges, which are nice opportunities for to promote other things like endurance, design, not only robotics issues, but also, you know, to broaden the scope of what a micro air vehicle system is. It's not only controllers or navigation, it's also, you know, transmission, sensors. We all know that, but that's nice to have those extra challenges. Not only that, but it's also, I guess, a nice opportunity for the organizer to put their own, you know, original aspects forward, and that's nice too. You know, to give a kind of peculiar, original challenge like that. The other thing I remember, I learned from organizing those events was that it is very difficult to write rules, because organizing a competition means you want to win that competition, and that's nice and that's normal. And the first thing you have to do as a competitor is to learn by heart the rules, because to try to understand what is the good strategy to win more points. And that objective is not always exactly the same as the objective that you had in mind when you start writing rules, and you said, okay, we want to promote the scientific community to work along that direction. And so that's just maybe an advice for all of us for future events, to take time to write rules in a proper way so that you will see what you really want to see. And that's always difficult. I think we all had the same experience in the past. And one thing I would like to add is that we, as in other events, we organized a virtual competition, which was, at that time, it was not driven by the pandemic. It was because we thought it would be nice to have that virtual competition, not only if the weather was not very good, so we have indoor competition plus a virtual competition. Not only that, but also because it is a good way to promote quite a lot of preparation work, like to send a message that before going to the airfield, you really need to simulate, to understand, to figure out where the obstacles are, to, you know, and that was really helpful. I think at the beginning I was not so in favor of that, but I must admit that I learned a lot from those virtual events as well. And again, I agree with Gauthier that it is nice to continue promoting not only multi-rotors, but also, you know, different kind of design, because there are different solutions for different missions. And that's, I like the way that IMAV is a place where people from different fields, aeronautical engineers, from electrical engineering departments, for different departments or different technical departments, they can they can get together and they can have something to share. And that is really something that is specific to IMAV, and I wish this will continue in the future.
Great, thank you, Professor. Definitely something we have to push and to keep in the IMAV events. So without any more delays, let me pass the word to Pascual, so he has also some time to share his experience, and then we can discuss a little bit more about these ideas. Please, Pascual, if you can go, Professor Pascual.
Thank you, Jose. Thank you, and good afternoon and good evening to everyone. So we in Madrid, in Spain, we were the last before the pandemic time that IMAV was real face-to-face competition, face-to-face paper presentation, face-to-face people networking and knowing each other. We were very, very happy at this time that the next one were going to be in Mexico, that we were going to meet there. And so that's what we have now. So that we are meeting as we are meeting. So, but we hope that we recover, take again the presential IMAV. That is more interesting because of everything, because of the human factor, because of the face-to-face knowing people, and because of the competitions that are. So I also agree with Jean-Marc that the simulation is a very, very interesting way of competing, but also real flights. We don't have to forget that we are preparing our teams, we are preparing our algorithms, we are preparing everything for going to the real life. So I have a short summary of what we did just a couple of months before the pandemic, and I'm going to share the screen. Okay, and let's go with the presentation. Yeah, the IMAV 2019 was located in Madrid, in Spain, and we choose one of the applications in which drones can be useful, and we choose in this case to use it for logistic. I mean, there are several. Traditionally in IMAV, we have always been thinking of more civil applications as the military applications, more visual inspection, or more search and rescue, or more things like this. More a little bit far from military. And there are many. The military, they have a lot of money. They push a lot the science, the algorithms, but we believe, and it's not that we believe, we are sure that now we have an explosion of civil applications with drones, and we are pushing in this way. We choose to have the logistic as the main motto of this year, and we went for the indoor competition. Indoor competition was in the middle of Madrid. This is the old building in which we have our faculty, our college, and we built a whole warehousing application with inventory, and also with delivery of packages. And we have to search for certain packages, to have an inventory. I mean, to know where the packages are situated, where they are located within the warehouse, and to pick some of them and to deliver them to where they should be. I'm going to mix some of the figures of the competition of the whole IMAV with the presentation. So we had 10 teams from 8 different countries, and of course we had 3 winners. We went to the outdoor competition. That is also very challenging. It's also related with logistic, that we were transporting several packages or several items to certain places, and that was close to Madrid, in the outdoors. We had also the same amount of teams and the same amount of countries, although they were not exactly the same. So we add all together, we have an overlap of several teams, but it's not a full overlap of all of them. We had conferences, papers. We selected 30 papers. 6 of them were nominated for the special and best paper award. We had 2 special issues, one from the IMAV and one from the US, from the managed systems. And here are the topics in which all the different papers were clustered. We have, the first system modeling and simulation, autonomy, also another mistake, autonomy of UAVs, industrial challenges. This is very interesting to have this, to see what are the different applications of what we are developing of the drones, intelligent navigation, the design of the UAVs, the perception of UAVs, and the flight control. These are the topics in which finally all the papers were clustered. We have 4 keynotes, a little bit of everything. That we have Airbus. What is the future, according to Airbus? What is the future of urban mobility using drones? We have also another keynote from the Spanish Research Institute in Aeronautics, for an important person there who was telling us where was the direction of this research. We have a very, very, very interesting keynote from a person who has been mentioned during several times. That is David Escaramuza in University of Zurich, telling us what is the future, what is his opinion or his point of view of the future of drone racing. And finally, we have another keynote regarding the European framework of regulations for the drones. And we have also a visit to the Aeronautics Museum in Madrid. I have to mention also the sponsors. The sponsor, we have 3 kinds of sponsors. We didn't achieve really to have many of them. We have the platinum, some of them that were traditional in the previous IMAV. They were not with us, but I have to thank a lot the Spanish post office, company, which is Correos, who was the main platinum sponsor. Also the gold sponsors, the Air Force Office of Scientific Research, who was also a gold sponsor. Parrot, who was also sponsoring. Airbus, and Aura. They were the 4 main, after the platinum one, the 4 main sponsors of the competition. And we have also another silver sponsor, Big Grace, who had a stand there, who was able to show all the participants, attendees, how the system is working in indoors. This
Recording
is the
in
indoor
progress.
competition, the outdoor competition. And these are several moments for both. This is keynotes, the trip to the outdoor competition, and explaining what was done there. Was, as I have said already, there was more focus on the package delivery. And it was also fixed wings, rotary wings, so hybrid vehicles. Yes, explaining more, I think, more the whole IMAV competitions than rather than this particular one. Some of the outdoors package delivery this time was in the right place. And this is the people who share the flying arena for us in the outdoor competition, and inviting to have an on the outdoor. I have another video more focused on the indoor, but I'm going to skip it because if the sound is not, I'm going to go very, very fast.
Are more oriented to the robotics field. But I knew IMAP because when I did my PhD in Bristol, I got to know Tom Richardson, who presented this morning. And I remember that one day when I was looking at his publications, I saw the name of the conference, and that stayed in my mind. So once I was in Mexico, when I came back to Mexico, I don't know how I bumped into the conference again. I think that was 2016, China. So they released the call for papers and competitions. And then I thought, oh yeah, I remember this. And I was curious. And I think Ben and his team, they did quite a nice work in publicizing the event, because they had this very nice video. So then we decided to apply, and we went to the competition, and it was a very nice experience. And it has been since then. But at that time, and right now, I am thinking that all of you were quite bold in organizing this type of competition, because it requires a lot of work. And apart from that, you don't offer money as a prize. And when you compare it to other competitions, similar competitions like TARPA, for instance, or more recently the MB Cirque, the one that Pascual participated, they offer huge amounts of money, and maybe that compensates for the amount of effort that teams have to put into, right? So having said all of that, because when we went to the competition as a junior team, we went because we were excited to go to China, and we wanted to get to know all of these technologies, not really because of the money. It was more like a scientific and technical thing. But having said all of that, what do you think is going to be the future of the IMAV competition, and of course the conference, when you compare it against this type of, or these other competitions that are also very attractive, and Alpha Pilot offer a lot of money as well. So what could you tell us about that, if you can? So please, whoever, who wants to start? Whoever wants to do that.
Yeah, so I think it's a very interesting remark. I would also be interested actually to know what the people attending the conference think. So yeah, personally, yeah, IMAV, I see it as a conference and competition. So really an exchange of ideas. And indeed, some of the people coming typically are like a bit more perhaps science oriented. Others are involved in the competition, but it makes for a very nice atmosphere in which people learn from each other. And it's not like super competitive in the sense like we don't want to say anything about our technology, because then you may win and get this money. And so it's, so yeah, I like this kind of exchange. Of course, it's obvious that there's a competition between these competitions in a sense, because if you have a lab and you want to do a competition, then yeah, it's a choice between, okay, do we try to join, I don't know, DARPA or something else, and then yeah, have a chance to win a lot of money, or do we join IMAV? And basically then in advance, you know, you will not win money. And so that I do realize, but yeah.
Thank you, Guido. Who else would like to comment on this?
Yeah, I have participated in both. In IMAV, I have participated several times since 2012 was the first time, 2000 next year, and so on. We have participated several times. Once we have also participated in the EMBA. This is a very, very high rewarded competition, and we got the third prize, but in the grand challenge, but we didn't get any money for that. So no, we got the money for participating. So we were in fact sponsored for participating only, and we were almost covering our participation. That was good. That was one of the reasons for going, because we had enough money for taking part on it. So what to say, or in which to participate? Of course, in both. IMAV competition is, yeah, the thing. The big difference, not only the money that they supply for the people, but another thing is the amount of UAVs and ground vehicles, and in this case, in this new embassy competition, is going to be also surface, so water surface vehicles, autonomous vehicles. So also we have to bring also robotic arms. So the whole scenario that we have to carry is much more bigger and much more expensive. So indeed, that is one of the reasons, because if they don't put money on these other competitions, perhaps they are not going to have so many people, because these are very, very costly. But in IMAV competition, so since this is a micro vehicle system, micro, that means that you can perhaps bring with you in the airplane, and it's not going to force you to spend a lot of money, at least in transporting and also in the vehicles that you are using. And that's why this is one of the reasons that you can participate in IMAV without. IMAV can be like having money for going to conferences. Do you have money in your team for going to conference? This is one conference in which you can not only present a paper, so that you can also demonstrate how things works in reality. So IMAV is very, very challenging, and there are not many UAVs competitions. In fact, so IMAV is a good choice.
Thank you, Pascual. Who else wants to go for this? Gautier.
Yes. I would say that IMAV is trying to find the correct balance between pure student competition and top researcher competition with high price and notoriety or whatever. So it means that it's more or less focusing PhD students and young researcher. And this is, I think, rewarding for PhD students if they can put a little part of their work during this early research life into practice. And the kind of tasks and missions that we ask, it's not easy, but it's not looking for outstanding performance either. And usually you can bring a little bit of what you are doing, and that could be swarming, and like for TU Delft, and their students, Kimberly, work on the small drones and get many points from that. So and we did the same more or less. So I think this level of competition is not that usual. Of course, it requires some time, energy, a little bit of money to prepare, but it's not always demanding for very expensive materials. And basically, as Pascual said, if you have enough money to send 5-6 people to a conference, which is already a lot, and to put some extra money into basic frames and so on, then you can compete if you are ready to put the time and energy. And again, for certain researcher or students, PhD students, that can be highly rewarding.
Thank you, Gautier. And last but not least, please, Professor Jean-Marc.
Yeah, I agree with Gautier and the fact that it has to stay open to students, because it's also a very good way to educate our students to take part in a conference and in a competition. So it means that also for the conference, it's nice to have maybe students presentations or posters, or some to accommodate some room for them, and so that you don't have on one side the high level conference for advanced or senior researchers, and on the other side competition for students, but they can go to both places, and that is really important to me. Also, the question of putting a very big prize on a competition the drawback I can see with that is you usually end up with a very professional team, which is going to select the most robust choices, not necessarily the most interesting in terms of advanced techniques or, you know, you don't want to take risk. You want to grab a lot of points. And okay, that's another perspective. I think that it is nice with IMAV that we have a university perspective, like you know, it's an academic atmosphere. And the nice thing I like in IMAV is that people tend to help each other, and they you know, they give a small electronic component that is when you come from Europe to Mexico, or from Mexico to Europe, okay, you have to you are happy to have some help from other people there. And I would be, I'm afraid that if you put too much money on the table, maybe people will tend to, you know, we might lose that nice atmosphere. That's my concept.
Yeah, that's for sure. It's something that I thought as well, because at the end of the day, it becomes like, I can imagine that teams who want to participate, they see it as an investment. They need to put money to win more money. I mean, there is nothing wrong with that, but then the pressure is different, right? So there is an academic pressure to get, you know, to show things. I remember once actually Guido told me that, I think in the IMAV 2017, that he said, we are very interested in showcasing what we are doing here, rather than talking about, oh, we want to win. It's so badly we want to win that, you know, and that stayed with me as well. So when you have this idea of we have to invest a lot to win a lot, then yeah, I can imagine that people get a lot of pressure. So we are running out of time, but I don't want to stop here. I would like to hear a bit more of what do you think are the next steps for the IMAV, or if you have a message that you want to share. I think we can take a few more minutes. So please, we start with you, Guido, if you want to comment something, please.